picture an island in Indonesia. Dense jungle, volcanic mountains, the kind of place that feels cut off from time itself. Now picture a human being standing about 3 feet tall. Not a child, an adult, fully grown, fully capable, living their entire life at a height most of us would associate with a 5-year-old. Now picture an entire species of these tiny humans surviving on that one island for roughly 700,000 years. That's not a typo. 700,000 years. To put that in perspective, modern humans, Homo sapiens, have only existed for about 300,000 years total. This tiny species was already ancient history in the making before our species even showed up. And then, based on everything we can currently piece together, they disappear. Not slowly fading into extinction over tens of thousands of years like most species do. The evidence suggests something closer to sudden, like someone flipped a switch. One moment they're there in the archaeological record, and then they're just gone. If you're using this to fall asleep, that's exactly why I make these. So subscribe maybe, and let me know in the comments where you're listening from and what time it is right now for you. I check these things constantly, and it's wild. Sydney at sunrise, Chicago at midnight, all listening to the same mystery at the exact same moment. Here's what we're actually dealing with. Scientists call them Homo floresiensis. The internet nicknamed them Hobbits the moment they were discovered. And honestly, once you hear the details, you'll understand why. 3 feet tall, brains roughly the size of a grapefruit. Yet somehow making stone tools, hunting massive prehistoric animals, and surviving on an isolated island for a span of time that dwarfs almost every other chapter of human evolutionary history. The questions here aren't small ones. Who were these people really? Were they a fully separate species or something stranger, some evolutionary branch we haven't fully mapped yet? How did their ancestors even reach an island separated from the mainland by open water? Water that would have required some kind of crossing that shouldn't have been possible for whoever came before them. How did a population this small, on an island this isolated, maintain genetic health, and survive for hundreds of thousands of years when small populations are usually a death sentence? And maybe most disturbing of all, what could make a species vanish after surviving that long? A volcano, a changing climate, or something else entirely showing up on their shores? I want to be upfront with you. This isn't a story with all the answers. Some of what we know is solid, backed by dating methods and fossil evidence that scientists have checked and rechecked, but other parts are genuinely contested. Researchers disagree, sometimes fiercely, about what the evidence actually means. I'll walk you through both what we know and what we're still arguing about, because that's the honest version of this story. If you want to listen to this without any music or ads interrupting the flow, follow me on Spotify. It's completely free, and the experience is just cleaner. And if you've got 30 seconds, a 5-star review helps this channel more than you'd probably guess. Links in the description. Now, let's go back to the discovery that started all of this. Because before the world knew anything about the hobbits of Flores, there was just a hole in the ground, and a team of researchers who had no idea what they were about to find. To understand how a 3-foot human could exist at all, you first need to understand the island that made them. Because Flores isn't just a random dot in the Indonesian archipelago. It's one of the strangest evolutionary laboratories on the planet, and once you know what island isolation does to living things, the hobbits start to make a disturbing kind of sense. Here's the basic principle, and biologists have known this for over a century. It's called island biogeography, and it comes down to one simple idea. Take away the mainland, take away the predators, the competitors, the vast resources of a continent. Put a population of animals on a small isolated landmass instead, cut off by open water, and watch what happens over enough generations. The rules of survival change completely, and when the rules change, bodies change with them. On continents, big is often good. Big animals can defend themselves, travel farther for food, survive lean seasons on stored fat, outcompete smaller rivals. But islands don't reward big. Islands punish it. Resources are limited. There's only so much food on a chunk of land surrounded by ocean. A massive body that needs massive amounts of fuel becomes a liability instead of an advantage. So, over generations, something remarkable happens. Large animals shrink. This is called insular dwarfism, and it's been documented over and over again across the world. Dwarf mammoths on Wrangel Island, dwarf hippos in Cyprus and Madagascar, miniature horses on islands in the Mediterranean. Nature isn't sentimental. If your body is too expensive to run on limited resources, evolution finds smaller, cheaper versions of you to keep the lineage alive. But here's the flip side, and this is where things get genuinely strange. While big animals shrink on islands, small animals often do the opposite. They grow, without large predators around to keep them in check, and with big competitors no longer hogging every resource. Smaller creatures can expand into ecological roles usually filled by giants. This is called island gigantism, and it's just as well documented as its opposite. Giant tortoises, giant flightless birds, and on Flores specifically, giant rats, some of them the size of a small dog, comfortably filling niches that would belong to foxes or badgers almost anywhere else on Earth. So on one single island, you get this bizarre inversion of normal biological scale. Big things get smaller, small things get bigger. The whole ecosystem recalibrates itself according to rules that don't apply anywhere else. And Flores didn't just experience this phenomenon once or in one species. It experienced it again and again, across multiple lineages, over millions of years, which raises an obvious question. If elephants could shrink on this island and rats could grow to the size of cats, what happens to a population of humans that gets stranded there too? To answer that, you need to know exactly what kind of island we're talking about. Flores sits in the Lesser Sunda Islands chain, part of Indonesia, roughly between Bali and Timor. It's a narrow, mountainous strip of land, maybe 200 miles long, dominated by active volcanoes and dense tropical forest. And critically, it has always been an island. Even during the depths of the ice ages, when sea levels dropped low enough to connect much of Southeast Asia into a single landmass called Sunderland, allowing animals and early humans to walk between what are now separate islands, Flores remained cut off. The waters separating it from its neighbours were part of a deep oceanic trench, and even at the lowest sea levels in the Pleistocene, that gap never fully closed. This matters enormously. It means that whoever or whatever reached Flores in the deep past didn't just wander over on dry land like they could elsewhere in the region. They had to cross open water. Every single wave of colonization, whether we're talking about elephants, rats, or hominins, required some kind of ocean crossing. Maybe deliberate, maybe accidental. Animals swept out on floating vegetation during a storm, clinging to debris until they washed ashore on Flores by pure chance. Either way, arrival on this island was never guaranteed and never easy. And once you were there, leaving wasn't easy either. Flores was a one-way ticket into isolation. That isolation is precisely why the island became such a breeding ground for evolutionary extremes. Populations that make it to Flores are cut off from the gene pool of the mainland. No fresh migrants arriving regularly to interbreed with. No easy way to leave if things go wrong. Just a closed system evolving on its own terms, generation after generation, shaped entirely by the specific pressures of that one patch of land. Over enough time, that kind of isolation can turn a population into something almost unrecognizable compared to its mainland ancestors. And Flores gave every species that arrived there decades, no millennia, to feel that pressure. The fossil record here is remarkable, Ancient dwarf elephants called Stegodon lived on Flores for hundreds of thousands of years, evolving down from their much larger mainland ancestors into island-adapted versions that would have stood as much as a third smaller. Giant rats scurried through the underbrush at a size that would make most people recoil, filling ecological gaps left by the absence of larger island predators. And prowling through all of it were Komodo dragons, the largest lizards alive today, apex predators that could grow to over 10 feet long and take down prey many times their own size. Flores wasn't some peaceful tropical paradise. It was a pressure cooker, an island ecosystem full of oversized reptiles, undersized elephants and outsized rodents, all locked into their own evolutionary experiments completely independent from anything happening on the mainland. This is the world that any human population arriving on Flores would have had to survive in. Not a gentle transition, not a slow easing into island life. A direct confrontation with an ecosystem already reshaped by hundreds of thousands of years of isolation, filled with predators and prey that followed none of the normal rules. Now here's why all of this matters so much for the story of Homo floresiensis, and why Flores has become one of the single most contested pieces of ground in all of human evolutionary science. If insular dwarfism can shrink an elephant, could it also shrink a human? Could a population of early hominins, perhaps something like Homo erectus, arrive on Flores at a normal height, then undergo the exact same evolutionary shrinking process that turned massive Stegodon into pony-sized versions of themselves? It sounds almost too clean, too perfect an explanation. And that's exactly why so many researchers have spent decades arguing about whether it's actually what happened. Because here's the complication. Human brains, unlike most other traits, don't necessarily shrink in the same proportion as body size when a species undergoes island dwarfism in other animals. Body size and brain size aren't always linked the way you'd expect. So the discovery of an incredibly small-brained, incredibly short human relative on this specific island, of all islands, immediately put Flores at the center of a much bigger question. Is this simply island dwarfism operating on our own family tree, exactly as it does on elephants and deer elsewhere in the world? Or does something about this particular case break the normal rules, hinting at a population with a much stranger and more ancient origin than a straightforward case of shrinkage? That question alone has fueled entire academic careers and heated conference debates for close to 2 decades. And we'll get deep into those competing theories later in this story, because the answer, or lack of one, cuts right to the core of who Homo floresiensis really was. But there's a second reason Flores matters so much, and it's just as important as the biology. This same isolation that could produce a unique surviving population is also exactly the kind of setting that could destroy one. An island ecosystem is a closed system, fragile in ways continental populations rarely have to worry about. A single major volcanic eruption, and Flores sits on some of the most active volcanic geology on Earth, could reshape the entire island's habitable landscape within days. A single disease outbreak has nowhere to dilute itself across a wider landmass. A single population crash has no neighbouring group nearby to replenish it. Everything that makes island isolation a breeding ground for evolutionary marvels also makes it a breeding ground for sudden, catastrophic extinction. So keep that duality in mind as we move forward. Flores is both a cradle and a trap. The very conditions that could allow a strange, small population of ancient humans to survive undisturbed for 700,000 years are the same conditions that could wipe them out in a geological instant, with almost no warning and almost no trace left behind. Whatever happened to the hobbits, good or bad, happened here on this island, shaped by these exact forces. And to understand how their story even began, we need to go back even further than the famous 2003 discovery, back to the very first humans who may have reached these shores at all. Long before anyone dug into the cave of Liang, and pulled out the bones of a 3-foot human, Flores was already telling a human story. Just not with bones, with rocks. If you go to the other side of the island, to a place called Matamenge and the broader Soa Basin in central Flores, you find something that looks, at first glance, disappointingly simple. Just a scatter of stone flakes, a few crude-looking cores, some broken animal bones. Nothing like a skull, no jaw with tiny teeth. Nothing you could point to and say, this is a person. But start putting those pieces into geological time, and the picture changes completely. The oldest stone tools on Flores go back at least 1 million years. Some researchers argue for dates closer to 1.3 million. These aren't ambiguous chips that might have been made by natural rockfall. They have sharp, deliberate edges, patterns of flaking, that you only get when a brain is hitting stone with a plan in mind. Beside them, you find butchered Stegodon bones with cut marks exactly where you'd expect someone to slice meat off a carcass or crack open long bones for marrow. That means that by roughly 1 million years ago, well before Homo sapiens, well before Neanderthals, there were hominins living on Flores. Not visiting, living, making tools, returning over and over to the same areas, processing meat from the same kinds of animals. And the tools keep showing up in younger layers, not in a single thin band, like one brief colonization that fizzled out, but in multiple horizons stacked through hundreds of thousands of years of sediment. Every time you go up in the sequence, you're moving forward in time, sometimes by tens of thousands of years between layers. And again, the rocks are there, flakes, cores. Simple, yes, but repeating. That repetition matters. Random shipwreck survivors don't leave the same kind of stone artifacts in the same basin for 1 million years. Storm-blown animals on a floating log certainly don't. What the Soa Basin and Matamenge record looks like is this. Some kind of hominin crossed open water to reach Flores incredibly early, and their descendants, or other hominins following similar routes, kept using at least parts of the island for a very long time. Now, if you spread those early tools out on a table, you wouldn't see anything that screams Hobbit. Technologically, they look a lot like the toolkits associated with Homo erectus elsewhere in Asia. Simple core and flake industries, sometimes called Mode 1 technology. No fancy hand axes, no finely shaped spear points, just practical general-purpose cutting tools. And that's the first clue to how persistent this occupation must have been. Simple tools aren't the same as thoughtless tools. To make them the way we see them in the Soa Basin, you have to know exactly which kinds of rocks to pick up from a riverbed. You have to understand where to strike them, from what angle, to get a predictable flake. You have to do it so many times that the technique becomes standardized. Archaeologists can look at a scattered site and say, these flakes were made using the same reduction strategy, probably by people who learned from each other. That's planning. That's teaching. And when you see it repeated in layer after layer, separated by long stretches of time, it starts to look a lot less like someone passed through here once, and a lot more like this basin was part of a stable home range for generations. But this is also where things get tricky. Stone tools are wonderfully durable. They survive floods, landslides, volcanic ash falls. They sit in the ground for 1 million years without rotting. Bones, especially small, fragile hominin bones, do not enjoy the same privilege. They dissolve, get crushed, get eaten, get scattered. So we end up with this frustrating asymmetry, a long, clear record of behaviour, and almost no bodies to match it to. That means a site rich in tools doesn't automatically tell you who made them. One species can replace another, adopt similar tool-making strategies, and you, 1 million years later, are left looking at essentially the same style of flakes and cores made by completely different hands. So when we talk about those early Matamenge and Soa tools, you have to keep two ideas in your head at the same time. One, they are strong evidence that hominins had reached Flores by around 1 million years ago, and that they were using at least parts of the island repeatedly across vast stretches of time. Two, they do not, by themselves, prove that the same lineage stayed put without interruption all the way down to the age of Homo floresiensis. Tools can persist even when the toolmakers don't. Still, even without complete skeletons, we can make educated guesses about who those early islanders were. The likeliest candidate, based on the timing and the kinds of tools, is Homo erectus, the widespread early human that had already reached Java and other parts of Southeast Asia by 1.5 million years ago. If you draw a line from known erectus sites in Java eastward, Flores is not absurdly far away. It's the next big step, but there's a problem, and it's the same one we ran into in the last section. The Wallace Line. Those deep water channels that never turned into dry land, no matter how low sea level fell. You could walk from mainland Asia to Borneo to Java during glacial maxima, but you could not walk to Flores. There was always a strip of open ocean in the way. So how did an early human like Homo erectus, with a brain smaller than ours and no metal, no sails, no written plans, get across? There are two main ideas, and both are uncomfortable in different ways. The first is accidental rafting. Picture a coastline hit by a massive storm or a tsunami from a distant earthquake. Whole chunks of forest get ripped from the shore, roots tangled with soil, vegetation piled into floating mats. If a group of hominins was unlucky enough or lucky enough to be on one of those mats when it tore free, they could be swept out to sea and carried by currents until they slammed into a new shore. For mice or lizards, this kind of sweepstakes dispersal is almost certainly how they reach isolated islands. Some researchers think the same thing could have happened to early humans. The second idea is more radical, deliberate water crossing. Not necessarily sophisticated seafaring with mapped routes and planned voyages, but at least the intentional use of floating logs, crude rafts, or simple watercraft to get from one visible island to another. The lesser Sunda Islands line up in chains. From some points, you can actually see the next island on the horizon. If early Homo erectus had even a rudimentary understanding that if we cling to this and paddle we can get over there, then repeated short crossings over generations could have carried them eastward one stepping stone at a time. Neither scenario is fully proven. We don't have fossilized rafts. We don't have an ancient harbour with Homo erectus boat parts. What we do have is the simple, stubborn fact that hominins were on Flores more than 1 million years ago, and there has never been a land bridge. Somehow they crossed water. Whether it was a 1 in a million accident that worked once, or a series of intentional crossings learned and repeated, we're forced to accept early humans as more capable around water than we used to think. And that brings us back to the core mystery: continuity versus replacement. If a Homo erectus-like population made it to Flores 1 million years ago, did they stay, slowly shrinking and changing under island pressures until, hundreds of thousands of years later, their descendants walked into Liang as hobbits? That's the continuity hypothesis. One long experiment in isolation, insular dwarfism operating over something like 700,000 years. Or did Flores see multiple waves of hominin arrivals? Maybe the first colonists died out, their tools buried under ash. Later, another population arrived, perhaps from a different source region, with slightly different anatomy but similar stone technology. They used the same kinds of rocks, left the same style of flakes, hunted the same dwarf Stegodon, but genetically they weren't part of a single unbroken line. Right now the ground gives us just enough evidence to say humans have been part of this island for a very long time, and not enough to say this is definitely one family story. The hobbits of Liang step into a landscape already haunted by these earlier, invisible islanders. When we finally meet them in the cave, tiny bodies, strange skulls, puzzling brains, we have to ask, are we looking at the end of an incredibly long, continuous island saga? Or at the last chapter of a much more tangled book written by several different human species who all, at different times, took the same impossible leap across the water? To answer that, we need to jump forward to 2003, to a small excavation in a cool, damp cave on western Flores, where a few strokes of a trowel suddenly turned this abstract debate into something unnervingly concrete. Liang doesn't look like the kind of place that would explode human evolution debates. It's a big, cool limestone chamber in the hills of western Flores, used for centuries as a local shelter and a church gathering place. When Indonesian archaeologist Thomas Sutikna and his colleagues started digging there in the early 2000s, they weren't hunting for a brand new human species. They were mostly interested in late Pleistocene archaeology, how early modern humans used caves in Indonesia, what kinds of tools they made, what animals they hunted. The expectations were modest. Maybe they'd find some Holocene burials. Maybe, if they were lucky, a few Pleistocene bone fragments, something to fill in the regional record. Then they hit the layer that would change everything. In September 2003, the team was excavating a deep trench they'd opened in the cave floor. As they went down through the sediments, they started finding bones of extinct animals, dwarf Stegodon, giant storks, giant rats. Good news already. It meant they were finally in older, undisturbed layers. And then, at about 6 meters down, came the first unmistakably human piece, a small skull fragment, then more pieces, then a jaw. At first glance it was confusing, the bones were tiny. The skull vault was low, the jaw was strange, no chin, teeth that looked worn but not child-sized. Someone suggested they might be dealing with the remains of a child. But the dental wear didn't fit. The sutures on the skull didn't fit. This looked like an adult, and yet the overall size was closer to a preschooler. As the excavation continued, more of the skeleton emerged. A partial cranium, the mandible, vertebrae, ribs, parts of the arms and legs. The pelvis, bones from the hands and feet, enough to reconstruct body proportions with unusual precision. When they laid out the pieces in the lab and started measuring, the numbers refused to behave. The individual they called LB1 stood roughly a metre tall, about 3'6". The brain volume, based on the cranial measurements, came out around 400 cubic centimetres. That's in chimpanzee range and well below even the smallest known Homo erectus. But the teeth were relatively small and human-like. The face was delicate, not like a juvenile ape. The pelvis and leg bones showed clear adaptations for bipedal walking. It was as if someone had taken a small-brained, very ancient hominin, shrunk the body, and then mixed in some oddly modern features for good measure. Word of a tiny human skeleton from Flores began circulating quietly in 2003, and then the formal announcement in 2004 hit like a shockwave. The initial papers argued that LB1 represented a previously unknown species of human, later named Homo floresiensis. The press called them hobbits, and the nickname stuck. But even before the media frenzy, the controversy among scientists was immediate, because here's the uncomfortable reality. Everything was hanging on one partial skeleton. LB1 wasn't a complete, perfect fossil. Parts were missing. Some bones were distorted by the weight of sediment. The context was good, undisturbed layers, careful excavation, but there was still just this one primary individual. With LB1, the team also found other hominin fragments in nearby squares and slightly different depths. Additional teeth, bits of jaw, some limb bones, but none were as complete as LB1, and scattered through the same and overlying layers were the artifacts and animal remains that sketched out a broader picture. Simple stone tools, flakes and cores reminiscent of those from Mata Menge, burned bone fragments, piles of Stegodon bones that looked suspiciously like butchering waste. So the scene at Liang around the time LB1 lived seems to have involved small-bodied hominins using basic core and flake tools, processing dwarf elephants and other island fauna inside and around this large cave. To some researchers that looked like a coherent behavioural package. A stable way of life matched to an unusual body form, potentially stretching back deep into time. To others it raised red flags. Could a single tiny skeleton really justify naming a whole new species? What if LB1 was a modern human with a growth disorder, some combination of microcephaly, dwarfism, or another developmental condition? Pathology can produce extreme forms. Maybe the cave was mainly used by Homo sapiens, and LB1 was just one unfortunate outlier. This is where it helps to understand how a single fossil can still change everything. Paleontology lives in the world of minimum evidence. We almost never get large samples. We get scraps, fragments, the occasional lucky near-complete skeleton. When something appears that sits far outside the known variation of any existing sample, when its combination of features doesn't fit neatly into any known box, it forces a re-evaluation. LB1 wasn't just small. The whole pattern of traits was wrong for known modern human disorders, wrong for Homo erectus, wrong for Australopithecus. You had a tiny body, an ape-sized brain, but wrists, shoulders and feet that in some ways looked more primitive than much older African fossils. And you had this on an island already known for a long, strange hominin history. Even if LB1 had turned out to be unique, a one-off oddity, its existence would still have demanded an explanation that went beyond just another modern human. You don't find a 3-foot-tall adult with a 400cc brain living among dwarf elephants and giant rats in late Pleistocene Indonesia and shrug. But the story didn't stop with that first skeleton. Over the next few seasons, more remains from Liang and, later, more fossils from Mata Menge and nearby sites would either reinforce the idea of a long-lived, small-bodied island lineage or complicate it severely, suggesting a deeper, more tangled evolutionary story than anyone expected. For now, though, in 2003, all anyone had was LB1, a handful of extra bones, and a cave layer full of tools and Stegodon. And that was enough to split the field almost overnight into two camps. Those who saw in Liang a genuine new branch of the human family tree, and those convinced it was a misread pathological modern. To sort out who was closer to the truth, scientists had to answer two urgent questions. How old, exactly, were these bones and the sediments around them? And just how far outside normal human variation was this strange little skeleton? That's where we go next. Before anyone could argue about what LB1 was, they had to agree on when it was. And that turned out to be much harder than it sounds. Caves are terrible and wonderful at the same time. They preserve things beautifully, bones, ash, plant remains, but they also behave like natural washing machines. Water flows in, sediments slump, animals burrow, humans dig pits, stalagmites grow, roofs collapse. Layers that look simple on a diagram can be a tangle of reworked material when you get your nose right up against them. Liang is no exception. When Sutikna's team first published on LB1, they had a clear story in mind. The skeleton came from what looked like a coherent layer about 6 meters down. That layer contained Stegodon bones, simple stone tools, and other hobbit-sized hominin fragments. Using a combination of methods available at the time, they proposed that LB1 was around 18,000 years old, and that similar remains might stretch to maybe 12,000 years ago. If that were true, it would mean a non-sapiens human species surviving on Flores until almost yesterday, side by side in time with early farmers in the Near East. The media loved that version. Hobbits lived until 12,000 years ago is catchy. It slots neatly into our mental timeline. Neanderthals fade out around 40,000 years ago, modern humans spread, and then here, hiding on an island, a relic population hanging on into the late Pleistocene. But the dating story didn't stay that simple. To understand why, we need to zoom in on how you actually date a cave like Liang. First, there's the obvious starting point: stratigraphy. The basic rule is straightforward: deeper layers are older than the ones above them, assuming nothing has mixed them up. Excavators at Liang recorded the sediments meticulously. The colours, textures, grain sizes, changes in composition. They mapped each artifact and bone in 3 dimensions. That gave a relative sequence. These Stegodon bones are older than those. This tool sits above that ash lens. LB1 lies below certain modern human materials. But stratigraphy only tells you older than and younger than. It doesn't give you dates in years. For that, you need absolute dating methods. Radiocarbon is usually the first tool anthropologists reach for. It measures the decay of carbon-14 in once-living material: charcoal, bone collagen, plant remains. The problem is, radiocarbon has a hard ceiling. Beyond about 40,000 to 50,000 years, there's so little carbon-14 left that the measurements blur into noise. You can't use it to date something to 100,000 years ago with any precision. At Liang, some of the upper layers do fall within the radiocarbon window, and those gave reasonably good ages for more recent occupations. But LB1 and the deeper Stegodon Hobbit layers sat below that reliable range. Radiocarbon couldn't pin them down, so the team turned to other clocks. One of the big ones is luminescence dating, often optically stimulated luminescence or OSL. The basic idea: mineral grains like quartz and feldspar store energy from background radiation while they're buried. When sunlight hits them, that stored energy is reset to 0. If you can measure how much energy is built up since the last time the grains saw daylight, you can estimate how long they've been buried. At Liang, luminescence dating was applied to the cave sediments themselves, not the bones. That means you get ages for the layers surrounding the fossils and tools. If the dating is tight and the stratigraphy is clean, you can say with some confidence this layer was deposited around X thousand years ago, plus or minus some margin. Therefore the material embedded in it is at least that old. Another tool in the kit is uranium series dating. This works particularly well on calcium carbonate. Things like stalagmites, flowstones, and sometimes the carbonate crusts that form on bones or surrounding sediments. As uranium decays into thorium at a known rate, you can use the ratio between them to estimate age. In Liang, uranium series measurements on cave formations helped bracket the ages of certain sediment packages. If a stalagmite layer above a fossil-bearing bed dates to, say, 60,000 years, you know the fossils below must be older than that. The challenge is stitching all these pieces into one coherent timeline, while accounting for the ways a cave can scramble its own archive. And Liang had been scrambled. As more seasons of excavation and more dating samples came in, inconsistencies started to show up. Some dates on bones didn't match the surrounding sediments. Some sediments turned out to be slumped material from older layers higher in the profile. At least one key piece of evidence for very young hobbits turned out to come from disturbed context. Around 2016, after a major redating effort, combining refined stratigraphy, new luminescence samples, and improved uranium series measurements, the timeline was quietly but profoundly rewritten. LB1 was no longer an 18,000-year-old neighbour of early farmers. The new work pushed the age of the skeleton back to roughly 60,000 to 100,000 years ago, with a commonly cited estimate around 70,000 years. The last clear evidence for Hobbit-like hominins at Liang, based on associated fossils and tool-bearing layers, seems to end somewhere between about 50,000 and 60,000 years ago. In contrast, the youngest occupation layers of the cave, with clear signs of modern humans, date to much later, tens of thousands of years younger than LB1. So you have to keep two timelines in your head at once: the age of the skeleton itself, and the age of Homo floresiensis occupation more broadly, as inferred from their characteristic fauna and tools. There's another layer of uncertainty: error bars. None of these methods give a single exact birthday. They give a range. This sediment was probably deposited 74,000 years ago, plus or minus 9,000. That means the true age could easily stretch across many human generations in either direction. So when researchers say hobbits vanished overnight, they don't mean literally one bad weekend. They mean that, in the archaeological record, a pattern that persists for tens of thousands of years. Hobbit-sized hominins, core and flake tools, Stegodon hunting stops abruptly at a certain horizon. Above that line, the fossils and artifacts look different. Something changed fast enough that, at the resolution of cave sediments and dating methods, it feels instantaneous. Exactly what that overnight looked like on the ground. For the last small groups of Homo floresiensis on Flores is another question entirely. To get closer to that, we have to look beyond dates and into bodies, into the anatomy that sparked a decade of fierce argument over whether LB1 really marks a separate species or a very unusual member of our own. When the first paper on LB1 hit the journals in 2004, the authors didn't hedge their bets. They called it a new species, Homo floresiensis. Not a weird modern human, not a diseased individual, a genuinely distinct branch of the human family tree with its own evolutionary history, its own adaptations, and a body plan that didn't match anything alive today. Almost immediately, other researchers fired back to them. LB1 didn't look like a brand new species. It looked like an outlier, maybe a Homo sapiens with a developmental disorder, or a case of severe microcephaly, or some other pathology that could shrink the brain and distort the skeleton. After all, creating a new species isn't something you do lightly. Taxonomy is conservative for a reason. So, for more than a decade, the debate circled around one fundamental question. Are we looking at evolution or illness? To understand why that question was so hard to answer, you have to look closely at the anatomy. Start with the basics. LB1 stood about 1.06 meters tall, around 3'6". The brain volume was about 400 cubic centimeters, comparable to a chimpanzee or to much earlier humans like Australopithecus. That alone is strange. A brain that small in a creature living 60,000 to 100,000 years ago, on an island with stone tools and big game hunting. It doesn't fit the usual storyline. Then you go bone by bone, and the picture gets even weirder. The skull has a low, receding forehead and thick cranial bones, more like Homo erectus than like modern humans. The jaw lacks a chin, again a primitive feature. The teeth are small and relatively modern-looking, which is surprising given the rest of the head. The shoulders sit high and shrug-like. The collarbones are short, and the upper arm bones have a curvature and muscle markings that look almost ape-like. The wrist bones are particularly telling. Several of them have shapes we associate with much earlier hominins, broad, blocky carpals rather than the more gracile, specialized forms found in Neanderthals and Homo sapiens. The pelvis is wide and flaring, reminiscent of fossils over 1 million years older. And then there are the feet, long, flat, with short big toes and a strange proportion of foot length to leg length. If you scaled LB1 up to modern human height, they'd have clown shoe feet. Taken together, the original Flores team argued, this mosaic of traits didn't match any known modern human population, pathological or healthy. It looked like a small-bodied descendant of an earlier human species, probably Homo erectus, that had been evolving in isolation on Flores for hundreds of thousands of years. Critics saw the same bones and told a different story. Maybe LB1 was a Homo sapiens with microcephaly, a condition that drastically reduces brain size and can alter skull shape. Or perhaps it was a case of Laron syndrome, a form of dwarfism involving growth hormone insensitivity. Others suggested endemic cretinism from iodine deficiency, which can stunt growth and affect brain and bone development. Still others argued for some unique combination of growth disorders limited to a small inbred island population. These pathology explanations gained traction for a few reasons. First, LB1 was just one individual. Paleontology has a long history of naming new species based on single odd specimens that later turn out to fall within the range of variation of known species. Second, we already know modern humans can vary a lot. If you compare small-bodied hunter-gatherer populations, tall pastoralists and individuals with various developmental conditions, you get a huge spread in brain size, body proportions, and skeletal shape. So the key question became, is LB1 outside that spread? To answer that, scientists did what they always do when anatomy gets weird. They went comparative. They measured LB1's skull, limb bones, wrist, pelvis and feet in obsessive detail. Then they compared those measurements to enormous datasets, healthy modern humans from many populations, known pathological skeletons from medical collections, Neanderthals, Homo erectus, early Homo, even Australopithecus. If LB1 were a modern human with microcephaly, for instance, you'd expect its skull shape to cluster with other microcephalic Homo sapiens. Several teams ran those analyses again and again. LB1 plotted off in its own space. Not just small human, but a different pattern altogether, especially in the base of the skull, the shape of the jaw, and the architecture of the brain case. Similar tests were run for proposed dwarfism syndromes. The limb proportions, joint surfaces and growth patterns in the bones didn't match documented cases. With endemic cretinism, you'd expect specific deformities in long bones and vertebrae that simply aren't there. Pathology can certainly make an individual unusual, but it usually does that by pushing some part of the anatomy away from the normal baseline of its species, not by turning back the clock and recreating a package of primitive traits last common in hominins hundreds of thousands of years earlier. That's the crux of the argument. LB1 doesn't just look odd, it looks old-fashioned. And then more bones started to show up. LB1 was never alone in the sediments. Even in the first season, the excavations uncovered additional limb bones and jaw fragments from other small-bodied individuals, at least some of them clearly adult. Over subsequent years, the team identified remains from multiple Hobbit-sized hominins, LB2, LB3, and others, spanning a range of ages. They weren't all carbon copies of LB1, but they shared the same general body proportions: short stature, small heads, robust limb shafts, long feet. That matters. One pathological skeleton can be an anomaly. A population of similarly proportioned skeletons, over multiple layers, is much harder to explain as a cluster of rare diseases, all with the same outcome, persisting over thousands of years. The post-2004 discoveries at other Flores sites only strengthened that impression. At Matamenge, in the Soa Basin, researchers unearthed even older fossils, tiny jaw fragments and teeth, about 700,000 years old, also from a very small-bodied hominin. Those remains are not identical to LB1, but they point in the same direction. Little humans, on Flores, far earlier than any plausible arrival of Homo sapiens. So by stacking anatomy across individuals and across time, the balance gradually shifted. The more comparative work was done, the more the pathology explanations struggled to fit all the data at once: skull shape, wrist structure, pelvic form, limb proportions, population pattern, and deep time. The idea of a separate species, an island lineage of Hobbit-sized humans, started to look less like a fantasy and more like the simplest way to connect all the dots. But even if you accept Homo floresiensis as real, one puzzle still looms large: that tiny brain. How do you reconcile a chimp-sized brain with stone tools, organized hunting and survival on a dangerous island for hundreds of thousands of years? To tackle that, we have to go inside the skull and ask a different question. What was that 400cc brain actually doing? First, let's put some numbers on the table. Most estimates put LB1's brain volume right around 400 cubic centimeters. Some reconstructions are a bit higher, some a bit lower, but we're in that range. For context, a typical modern human sits somewhere between 1,200 and 1,500 cc. Neanderthals often exceed us, up around 1,600 cc. Chimpanzees average about 350 to 400. So on raw volume, the Hobbit brain is basically chimp-sized. If all you knew was that number, and you'd never heard of Flores, you'd probably file LB1 mentally next to very early humans like Australopithecus or the earliest Homo. Simple stone tools, short lives, limited social complexity. But we don't just have the number, we have the context. We have stone tools stretching back hundreds of thousands of years on Flores. We have evidence of big game butchery, repeated use of particular sites, possible use of fire. That combination forces a more careful question. What does 400cc actually mean? Brain volume by itself is a blunt instrument. It correlates with some things on average. Bigger brains in mammals do tend to support more flexible behavior. But it's not destiny. What matters at least as much is how that tissue is arranged. Which regions are expanded, how densely neurons are packed, how the wiring is laid out. That's where endocasts come in. Paleoanthropologists make virtual molds of the inside of the skull, either physically or with CT scans, to infer the outer surface of the brain. You don't get every sulcus and gyrus, but you can see overall shape, proportions and the relative expansion of different lobes. When researchers did this for LB1, they got a surprise. The floresiensis brain is tiny, yes, but it's not just a scaled-down chimp. Parts of the frontal and temporal lobes look relatively well developed for its size. Some analyses have even suggested reorganization similar in some respect to early Homo erectus or even Homo sapiens, crammed into a much smaller package. Not everyone agrees on the fine details. Endocast interpretation is notoriously tricky, but there's a rough convergence on one point. The Hobbit brain doesn't look like a random pathological shrinkage of a modern human brain. It looks like a small brain that has been shaped by selection. In other words, not just less, different. This is where behavior comes back into the story. What can we reasonably infer from what these brains actually did on Flores? Take the tools, the stone artifacts from Liang and older sites like Matamenge are often classified as simple flakes, cores, some points, nothing like the elaborate blades and bone tools of later Homo sapiens. But simple here is deceptive. Even basic flake tools require knowledge of raw materials, an understanding often unconscious of fracture mechanics, and the ability to teach or imitate techniques reliably across generations. Then there's hunting. The association of Hobbit remains with butchered Stegodon bones suggests coordinated exploitation of large prey. Whether they were actively hunting or aggressively scavenging, either scenario implies planning, group cooperation, and a sense of landscape, knowing where animals move, when they're vulnerable, how to access carcasses without being killed by them or by Komodo dragons. The possible use of fire is more controversial. Some layers at Liang have burned bones and charcoal, others don't. There's an ongoing argument about whether Homo floresiensis was regularly controlling fire, only occasionally using natural fires, or not using it at all. Each scenario has different cognitive implications. Regular fire control points to planning, knowledge of fuel, maybe even cooking traditions. Lack of fire would suggest they were solving survival problems in other ways, through shelter, clothing, social organization. What we can say is that these hominins managed to occupy Flores repeatedly in a predator-rich environment over enormous stretches of time. That alone speaks to some kind of durable cultural knowledge, not just individual cleverness. To make sense of that, researchers often reach for comparisons. Among fossil humans, Homo naledi in South Africa is one example that complicates the big brain equals big behavior story. Naledi also has a small brain, around 500 cc. Yet there are claims, still debated, of deliberate body disposal deep in caves, maybe even fire use. Early Homo erectus had brains smaller than ours, but managed long-distance dispersal, persistent hunting, and complex tool traditions. Among living primates, the picture gets messier still. Capuchin monkeys with brains dramatically smaller than any hominin routinely use tools, crack nuts, and show cultural variation between groups. Corvids, crows, and ravens with very different brain architecture altogether solve multi-step puzzles and remember human faces. None of these are direct analogies to Homo floresiensis. They don't hunt Stegodon or nap stone like our hobbits did, but they all point in the same direction. Behavior can be surprisingly sophisticated, even when brain volume looks unimpressive on paper. Neural density, circuit layout, and developmental history all matter. So where does that leave us with the hobbits? It's unlikely that a 400cc brain, no matter how well organized, could support the full range of symbolic thought, language complexity, and technological explosion we see in later Homo sapiens. There's no convincing evidence of art, ornaments, or elaborate ritual at Liang. If Homo floresiensis had language, it may have been simpler than ours. If they had myths, we have no trace of them. But not like us is very different from simple or stupid. The most plausible reading of the evidence right now is that Homo floresiensis had a brain tuned to the problems that mattered on Flores, navigating rugged terrain, remembering waterholes and fruiting trees, coordinating hunts, avoiding predators, managing social relationships in small groups, and maintaining tool traditions over generations. A brain that was small but specialized, efficient where it needed to be. Could we be wrong? Absolutely. New discoveries, a clearly associated hearth, a more complex tool assemblage, or in a dream scenario, preserved DNA revealing genes linked to neural development could push us to revise their cognitive profile up or down. For now, though, the safest position is a modest one. Homo floresiensis was not a miniature Homo sapiens trapped in a tiny skull, but neither was it a mindless relic. It was a different kind of human intelligence, scaled to a smaller body and a smaller brain, but evidently good enough to survive, and even thrive, on a demanding island for an astonishing length of time. And that raises another question. If you can pack that much survival ability into such a small frame, how do you get there in the first place? What kind of evolutionary journey could sculpt a lineage into hobbits? To answer that, we have to zoom out from the skull and look at the island itself, and at what isolation does to bodies over deep time. On big continents, evolution often rewards bigness. Larger bodies intimidate predators, store more energy, travel farther for food. But on small islands, the rules flip. If resources are tight, plants patchy and droughts regular. Being big can turn from an advantage into a liability. Large animals need huge amounts of food and water just to break even. When the island goes through a lean season, the giants are the first to feel it. That's where insular dwarfism comes in. Over many generations, natural selection on islands often favours individuals who can get by on less. Smaller bodies use fewer calories, reach adulthood faster, and often have shorter gestation times. When a population is trapped, no way to migrate to better pastures, those small efficient bodies can be the difference between surviving a bad decade and blinking out entirely. We see this pattern over and over again. On Mediterranean islands, elephants the size of ponies. On the Channel Islands off California, pygmy mammoths. On Crete and Cyprus, hippos that shrank down to the scale of big pigs. Dwarf deer, dwarf bison, dwarf everything. Same basic animal, different body plan, tuned to an island budget. Flores is no exception. In fact, it might be one of the best natural laboratories for this process on Earth. When you walk through the fossil record of Flores, you don't find a normal continental ecosystem. You find a hall of mirrors, where evolutionary rules have been bent by isolation. The Stegodon, an elephant relative, that the hobbits hunted is already a downsized version of its mainland ancestors. Giant rats got bigger, lizards like Komodo dragons got enormous, some birds ballooned in size. Large herbivores shrank, some predators and omnivores grew. This mix of miniatures and monsters is exactly what biologists expect when an island has been cut off for a very long time. So when researchers first realized just how small Homo floresiensis was, the island dwarfism explanation came almost automatically. Maybe, the argument goes, you don't need a totally separate, tiny-brained human lineage to explain the hobbits. Maybe you just need a normal-sized ancestor stranded on a resource-poor island for a few 100,000 years. In that version of the story, the starting point is Homo erectus. We know erectus was in this general region early. There are erectus fossils on Java by at least 1.5 million years ago. Stone tools on Flores go back to around 700,000 years ago, and at Matamenga those tools are associated with hominin remains that are already small-bodied but still older than the Liang hobbits. Put the pieces together, and one plausible scenario looks like this. A group of Homo erectus, tough, mobile, capable of crossing water gaps somehow, reaches Flores in the deep past. Maybe they island hop from the Asian mainland. Maybe they're pushed by climate shifts following prey and coastlines. However they get there, once they arrive, they're stuck. The deep water channels around Flores act like a moat. On that island, in a world of limited plant biomass, scarce big game, and frequent environmental swings, big-bodied erectus faces relentless pressure. Individuals who are a bit smaller, who can tolerate slightly longer gaps between successful hunts, who can reproduce earlier, leave more descendants. Over tens of thousands of years, then hundreds of thousands, those tiny advantages accumulate. This is not hypothetical hand-waving. We have good evidence from other mammals that dramatic size changes can happen surprisingly fast on islands, on the order of tens of thousands of years, sometimes even less. When a large animal suddenly finds itself in a new environment with strong selection pressures, body size is one of the traits that can shift relatively rapidly. If that's true for elephants and hippos, why not for humans? But scaling down a body isn't as simple as turning a knob. Some parts shrink easily, others don't. And this is where the island dwarf hypothesis for Homo floresiensis runs into its hardest questions. First, speed and magnitude. Could Homo erectus, with a brain around 800 to 1000 cc and a stature maybe 1.5 to 1.8 meters, really dwindle down to a 400 cc, 1 meter tall hominin in the time available? Many evolutionary biologists say yes in principle. Given a few 100,000 years and strong enough selection, that kind of change is within the realm of known mammalian plasticity. The sticking point isn't so much the overall size, it's the proportions and the details. Some aspects of floresiensis anatomy, like the shape of the wrist bones, the flare of the pelvis, and features of the feet, look to some researchers more primitive than Homo erectus. They resemble much earlier hominins, closer to Australopithecus. That's harder to explain by simple dwarfing. Shrink an erectus and you expect a mini erectus, same general blueprint, just scaled down, maybe with some tweaks. You don't necessarily expect older-looking traits to reappear. Could selection for climbing ability, or for moving efficiently over rugged terrain, favour a more primitive foot or shoulder? Possibly. Evolution doesn't have a rule that says you can't converge on earlier-looking solutions if they work in a given environment. But every such trait has to be justified by a plausible functional story, and not everyone is convinced all of them can be. Then there's the brain. If you shrink body size, brain size usually shrinks too, but not always in lockstep. Some dwarf mammals keep relatively big brains. In Homo floresiensis, though, the brain is very small, even for the reduced body size. Is that just extreme island thriftiness? Or does it hint at a lineage that branched off before Homo erectus fully ramped up its brain expansion? These uncertainties are why the island dwarf model, while elegant, doesn't have unanimous support. On one side, you have a clean narrative that slots Flores neatly into patterns we already understand. Big ancestor arrives, island squeezes it down, you get a small, efficient island human that still carries the cognitive toolkit of erectus in a reduced package. On the other side, you have anatomical oddities that don't fit comfortably into a simple shrink-ray scenario. Most researchers today treat insular dwarfism as a serious, live hypothesis for Homo floresiensis, not a fringe idea, and not a solved one either. It's attractive because it ties the hobbits to the known dispersal of Homo erectus across Asia, and because Flores itself shouts island evolution from every bone we dig up. But to really decide whether dwarf erectus can get you all the way to Homo floresiensis, we need to look beyond size alone. We have to ask whether the hobbits are just tiny descendants of a familiar ancestor, or whether their odd mix of traits points to something deeper in our family tree. That's the debate we turn to next. There's another way to read those strange proportions. Instead of starting with Homo erectus and shrinking it down, some researchers flip the story completely. They argue that the hobbits of Flores might come from a much deeper, more primitive branch of the human family tree, one that split off before erectus ever appeared. In this version, Flores isn't just an island that shrank a modern-looking ancestor. It's a time capsule, a place where an ancient kind of hominin, small-bodied and small-brained from the start, managed to hang on for hundreds of thousands of years while their cousins elsewhere evolved into taller, bigger-brained forms. Why even consider that? Because some parts of Homo floresiensis don't just look weird for erectus. They look, in key ways, closer to hominins that lived 2 million years ago in Africa than to anything in Asia 1 million years later. Take the wrist, the tiny wrist bones of LB1, the best preserved hobbit skeleton, have shapes and joint surfaces that resemble those of Australopithecus and early Homo, species like Homo habilis, more than Homo erectus or modern humans. The structure of the trapezoid bone, for instance, suggests a hand still partly tuned for powerful grasping, not the fully refined precision grip you see in later Homo. The shoulder girdle sits high and shrugged, with the scapula angled in a way that hints at frequent overhead arm positions. Again, more like early hominins that divided their time between ground and trees. The humerus and clavicle proportions reinforce this image of a body that might have been comfortable climbing, not just walking. The pelvis is broad and flared, with a shape that recalls Homo erectus, but also reaches back toward even earlier forms. The femur and tibia are short, but their cross-sectional geometry suggests a gait that wasn't simply a scaled-down modern human stride. The foot, famously, combines a long, flat shape with relatively short toes, but with an ankle and midfoot that, to some anatomists, look surprisingly archaic, more like something you'd expect around the time bipedalism first stabilized, not in a late Pleistocene island dweller. Line all these up, and one interpretation goes like this. This isn't a miniaturized, advanced human. It's a descendant of something that branched off early, perhaps around the time of Homo habilis or another small-bodied African form, that somehow left Africa, made it to Southeast Asia, and then became marooned on Flores. That raises an obvious problem: movement. If you invoke a deeper lineage, you now have to explain how a very early, relatively primitive hominin managed to cross the same water barriers that make erectus such an impressive traveller. It's one thing to imagine Homo erectus, with its taller body, longer strides, and larger brain, building crude rafts or exploiting currents to island hop. It's another to picture something habilis-like doing it. Yet the stone tools on Flores, going back to about 700,000 years ago, and possibly earlier, tell us that some hominin crossed those deep water channels long before modern humans. Wallace's line isn't a hypothetical. You can see it on a bathymetric map. Even at the lowest sea levels, Flores is separated from the Asian mainland by gaps that would have required intentional or accidental sea crossings. So the migration challenge cuts both ways. Any ancestor of Homo floresiensis, whether erectus or something more primitive, had to be capable of at least occasional water crossings. If we accept that for erectus, we at least have a known, wide-ranging species to point to. If we posit a deeper lineage, we're adding a ghost population, an early voyaging hominin for which we currently have no direct fossils outside Africa. That's where discoveries elsewhere start to matter. Over the last couple of decades, paleoanthropology has been blindsided more than once by late surviving archaic humans. Homo naledi in South Africa, small-brained, primitive-looking hands and shoulders, but maybe as recent as 250,000, 300,000 years ago. Homo luzonensis in the Philippines, tiny body, curved toe bones, odd dental traits, living possibly as late as 50,000, 70,000 years ago. In both cases, you have hominins that preserve surprisingly ancient-looking traits long after you'd expect them to be gone. Luzon is especially relevant. Like Flores, it's on the far side of deep water channels. Whatever got to Luzon had to cross open sea, just as on Flores. And there too we see a small-bodied odd mix hominin, whose ancestry is still unclear. That parallel makes the idea of ancient island-trapped lineages a lot less outlandish than it once seemed. Add Denisovans, known mostly from DNA, not bones, lingering in Asia, and the story that Asia was inhabited by a single tidy Homo erectus line until modern humans arrived looks increasingly naive. The region seems more like a patchwork of overlapping, sometimes hybridizing populations, some of them surprisingly archaic. All of this nudges the ancient branch hypothesis for Flores from wild speculation towards something that at least fits the broader pattern. Multiple human lineages coexisting, some with very old traits, some persisting shockingly late. But plausibility is not proof. What would it take to really decide whether Homo floresiensis comes from a deeper branch instead of dwarf erectus? First, more fossils from the right time windows. The Matamenge finds already hint at earlier. small-bodied Flores hominins around 700,000 years ago, but they're fragmentary. A skull or even good jaws and limb bones from those older levels could show whether the primitive features were already present long before the Liang hobbits. If they were, that would strengthen the case for a distinct lineage, rather than late-stage dwarfing. Second, fossils from in-between places. If an ancient branch wandered out of Africa and into Southeast Asia, we might expect to find similar-looking hominins on other islands, or even on the mainland, in deposits around 1 to 2 million years old. Right now, we don't have that. We have erectus on Java. We have earlier African forms, and a big geographic and anatomical gap in between. Third, genetic data. Ancient DNA from tropical caves is a long shot. Heat and humidity shred DNA quickly. So far, no genetic material has been recovered from Homo floresiensis. If that ever changes, if a tooth or petrous bone yields sequenceable DNA, we could compare it directly to erectus, Denisovans, Neanderthals, modern humans, perhaps even Naledi. A clear, deep split would clinch the ancient branch idea. A closer affinity to erectus would push us back toward the dwarfing model. Right now, that decisive evidence is missing. We're working with anatomy, stone tools, and the broader context of what other hominins were doing. Those lines of evidence can suggest. They can make scenarios more or less likely, but they can't yet tell us, with confidence, whether the hobbits are tiny descendants of a known traveller or the last isolated representatives of an even older world. Until we fill in those gaps, Homo floresiensis sits in a kind of evolutionary limbo. The bones whisper of deep time, the island shouts dwarfism, and the rest of the human fossil record keeps reminding us that reality doesn't have to pick just one tidy story. To really understand these people, you have to zoom in. Not on their bones, but on their home. Liang is not just a cave with some fossils. It's a particular kind of place, doing a particular job, for a very long time. And that job tells us something about how hobbit life was organised, season by season, year after year. Caves, from a hominin point of view, are cheat codes. They moderate temperature. Step inside Liang and you're partly insulated from the brutal afternoon heat and the chill of night. They shield you from wind and at least some rain. They offer a defensible space, one main entrance, limited angles of attack, solid rock at your back instead of dark forest. Most importantly for us, they preserve things. Out on an open floodplain, a campsite is like writing on a beach at low tide. Rain, roots, burrowing animals and later humans wipe the slate clean. In a cave, layers of dust, ash and sediment slowly bury what people leave behind. Hearths collapse, bones get trampled and broken, stone tools snap and scatter. Over tens of thousands of years, all of this stacks up into a stratified archive. That's what Liang is, not a snapshot, but a heavily edited, compressed history of repeated visits. Archaeologists read that history by looking at patterns in the debris, not just the objects themselves. Where are the stone tools densest? Are they clustered near what looks like an ancient hearth, or near the back wall? Are the broken animal bones concentrated in one part of the cave, suggesting a butchery area, while other zones are oddly clean, maybe used for sleeping? They look at ash lenses, thin, dark, charcoal-rich layers, and ask, is this a single fire event, or a floor caked with dozens of small hearths over centuries? They track how these zones shift up and down through the layers as the cave slowly fills with sediment, like watching the furniture in a house get rearranged over time. At Liang the distribution of artifacts and bones suggests repeated, organised use, not random one-off sheltering. You see areas with stoneworking debris, areas where animal bones were cracked for marrow and cooked, and quieter zones with fewer sharp edges and less trash. That's the archaeological fingerprint of people who weren't just ducking in during a storm, they were structuring their space. So how many of them were there at any given time? This is where we have to be careful. You can't just count bones and say, 12 individuals, therefore a group of 12. Many of those bones accumulated over thousands of years. Some are from people who never met each other. But we can triangulate from hunter-gatherer ecology and the scale of the site. A cave the size of Liang doesn't comfortably hold 100 permanent residents. Air quality, waste build-up, conflict over space, those problems show up fast. Most researchers picture small bands using the cave, maybe 10, 15, 20 individuals at a time. A handful of related families, plus whoever married in. Did they live there year-round? Probably not in the modern house sense. Think more like a seasonal base camp that keeps getting reused. Flores is wet, steep, and carved up by rivers. Seasons matter. There are wetter months when streams swell and slopes get slippery, and drier months when water retreats and some areas become hard to exploit. The cave's location makes sense in that context. It sits above a valley with access to water, within reach of good hunting grounds and plant resources, and not too far from sources of stone. That last part is crucial. Stone tools don't just appear. The raw materials have to be carried in. When archaeologists analyse the rock types in the Liang tools, they can often trace them back to specific outcrops or riverbeds. If most of the stone is local, that suggests a group whose daily foraging radius was centred on this landscape. If some of it is coming from farther away, that means mobility, people moving across the island, revisiting the cave as part of a larger seasonal circuit. The pattern at Liang looks more like the second scenario. The cave seems to sit at a crossroads, reliable water down in the valley, stone sources within a walk, and routes out to where the small elephants and giant rats lived. In that sense, the location is not random, it's strategic. This is what we can say with some confidence. Hobbits used Liang repeatedly over many thousands of years. They organised their activities within the cave. They likely came in small groups, and the cave's appeal was tied to water, raw materials, and access to food-rich zones. What we can't say, at least not honestly, is exactly how they timed their movements, how long a typical stay lasted, or whether specific parts of the cave were sleeping areas in the way we think about bedrooms. We can infer patterns from ash and bones. We can compare them to modern foragers who cycle through a landscape, hitting the same key spots each year when certain fruits ripen or certain animals migrate. But we're always one step removed, reading behaviour through rubble. Still, that rubble tells us this. Life at Liang wasn't a desperate scramble in a random hole in the rock. It was part of a deliberate survival strategy tuned to an island's seasons, its water, its stone, and its strange mix of animals. And those strategies show up again when we look at what they were doing with the stone itself. Because once you start examining the tools they made in this cave, a different picture emerges, one that forces us to rethink what simple technology really means. If you just glance at the tools from Liang they don't look like much. No delicate blades, no bone harpoons, no carved figurines, just chunky flakes, simple points, and battered cobbles. The sort of thing that in an old-fashioned textbook might get dismissed as primitive. But that's the trap. On Flores. Simple doesn't mean stupid. It often means this works, so don't mess with it. Let's start with what's actually there. Across the key layers at Liang you see a core and flake technology. People pick up a suitable cobble, usually volcanic stone from local streams, knock off sharp flakes, and use both the flakes and the remaining core as tools. There are big cutting flakes, the sort you'd use to slice through hide or dismember a carcass. There are smaller, more standardized flakes, shaped enough to give a consistent edge for tasks like scraping, cutting tendons, or processing plant fibers. Some cores are heavily reduced, with flake scars all around, suggesting careful, economical use of each stone. You also get unifacial and bifacial points, flakes retouched along one or both edges into tip-like forms. They're not elegant javelin heads, but they'll punch into meat. Add in edge-damaged flakes that look like they were used as knives or scrapers, plus hammerstones and anvils with pitting and wear from pounding and cracking bones. Zoom out beyond the cave and you see a similar picture at other Flores sites, including the older deposits at Mata Menge. Simple flakes, small cores, basic points, battered cobbles. The same general technological language persists for hundreds of thousands of years. To make any of this, you need more than opposable thumbs. Even a basic flake requires planning. You have to select the right raw material, hard, fine-grained enough to fracture predictably. You need to envision the shape inside the cobble and strike at just the right angle and force to detach a usable shard instead of shattering the rock. At Liang, many flakes show controlled platforms and consistent angles. That tells you these weren't random bashes. Toolmakers knew where to hit, how to hold, how to rotate a core as it got smaller. That's practiced motor skill, refined over years of repetition and observation. There's also time investment you never see in the finished object. Someone had to walk down to the river, search for the right kind of stones, haul them back up to the cave. In a small-bodied hominin with limited energy reserves, carrying weight uphill isn't trivial. Doing that repeatedly means you've already decided in your head that stone technology is worth the cost. And once you've got those cobbles, you don't just smash them any which way. In some layers, cores were transported whole and only napped inside the cave. That's a conscious decision to bring packages of potential tools into a central place, then break them down as needed. It's a kind of mobile toolkit strategy, scaled to a 3-foot body. The continuity of this technology is one of the most striking things. For hundreds of thousands of years, from the earliest evidence of hominins on Flores to the later Liang hobbits, the tools stay broadly similar. Flake and core, small points, battered hammerstones. There's variation in size, raw material use and details, but no big leap to blades, microliths or complex composite weapons. One interpretation is stagnation, they never advanced. Another, increasingly favoured view is stability. The island problems stayed basically the same, and so did the solutions. Flores offers a consistent menu. Small elephants, giant rats, lizards, birds, nuts, tubers, shellfish along the coasts. No huge herds migrating across open plains. No need for long-range projectiles to bring down galloping antelope. In that world, a reliable close-range toolkit can be good enough for a very long time. Keep in mind, complicated isn't always better. A razor-thin blade is amazing until it snaps. On steep, wet slopes or in dense vegetation, you might prefer chunky, durable edges you can resharpen endlessly. If your prey is often trapped in ravines, bogged in mud, or ambushed at close quarters, you don't need a technological arms race. You need something that works every time, and that you can teach a teenager to reproduce without a semester-long course. But here's the uncomfortable question. Do these tools actually belong to Homo floresiensis? Stone tools don't fossilize with a label. The flakes at Liang are found in the same layers as hobbit bones and butchered animal remains, which strongly suggests a connection. At Mata Menge and other older sites, you get similar tools but no hobbit bones, just ancient sediments and extinct fauna. Some researchers argue that an earlier species, maybe Homo erectus, maybe something even more archaic, brought this core and flake tradition to Flores long before the hobbits we know from Liang. Over time, that founding population shrank in body size under island pressures. but kept the same overall tool-making style. In that view, what we call Hobbit tools are actually the long conservative tradition of a lineage that starts far earlier on the island. Others point out another possibility. Modern humans were definitely in Southeast Asia by the late Pleistocene, and their tools, in some contexts, can also be surprisingly simple. At Liang, the youngest layers show a technological shift that lines up with Homo sapiens. But what about the uppermost Hobbit layers? Could there be overlap, with more than one species using broadly similar flake-based technology? Right now, most evidence lines up with this. The tools in the Hobbit-bearing layers were almost certainly made and used by the same population as the bones. The older tools at sites like Matamenge probably belong to their ancestors, whether we call those ancestors early H, floresiensis or something else. But that almost is important. Without a Hobbit hand clutching a flake, there's always a sliver of doubt. Even with that uncertainty, the tools tell us a lot about how these small humans made a living in their strange island ecosystem. The presence of standardized cutting flakes and points combined with cut marks on Stegodon bones fits a picture of active carcass, processing, skinning, disarticulating joints, filleting meat. Some bones show spiral fractures from being snapped when fresh, a classic sign of marrow extraction. That's calorie-dense fat, exactly what a small, energetically constrained hominin would prize. Simple points could have been used as thrusting spear tips, or as handheld stabbing implements at very close range. On an island where large animals are relatively slow, and not as fast to flee as African antelope, close-quarter hunting becomes plausible. A small group could drive a Stegodon into a trap, wound it repeatedly, then finish it off with repeated thrusts and stone-assisted blows. The same toolkit works beautifully for scavenging. If a Stegodon dies in a ravine, or is brought down by a crocodile or a rockfall, the first hominins on the scene can strip meat and crack bones far more efficiently than any other scavenger. Speed matters, stone edges win, and it's not just meat. Those same flakes can peel bark, scrape hides, open tough plant husks, and process fibres for cords or bindings. Hammerstones can pound tubers to make them more digestible, or crack open the bones of giant rats after roasting. A few basic tool types used flexibly can plug into almost every part of the island's food web. So when you hold one of these Liang flakes in your mind, don't imagine a failed attempt at real technology. Imagine a 3-foot human standing in a cave doorway, rotating a cobble in their hand, striking just so, then walking out into a landscape of steep green slopes and miniature elephants, carrying in their palm a shard of stone that has, for hundreds of thousands of years, been exactly sharp enough. In the next section, the question becomes, sharp enough for what kind of fires, what kind of cooking, and what kind of life in the half-dark of that cave? Because once you start looking for fire on Flores, the story gets even murkier and even more revealing. If you want to know how sophisticated a prehistoric group really was, you don't just look at their stones, you look for their fires. Fire is one of those turning point technologies. Control it and your whole world changes. What you can eat, where you can sleep, who can live long enough to tell stories. Lose it or never quite master it, and you're bound to the rhythms of daylight and raw food. So did the hobbits of Flores really command flame inside Liang? Or are we seeing something messier, more intermittent, more fragile? Archaeologists don't get to see dancing flames in the record. They get crumbs. The first thing they look for is charcoal. Tiny black fragments of burned plant material embedded in the sediment. Under a microscope, you can sometimes still see the cell structure of the original wood, just converted to carbon. If you see clusters of charcoal pieces in discrete patches, that's a hint of hearths. Then there are burned bones. Bone that's been exposed to fire changes colour and texture in telling ways. At lower temperatures, it turns brownish or dark grey, sometimes with cracking on the surface. At higher sustained temperatures, it can go bluish-white and become chalky and brittle. A pattern of bones heated enough to cook meat, but not enough to incinerate. Everything suggests controlled domestic fires rather than random bushfires. You can also get hearth features, lens-shaped patches of reddened or blackened sediment, concentrations of ash, burned stone fragments that were used as pot boilers or just happened to be sitting under the fire. In some caves you see stacked layers of these features through time, like living room fireplaces rebuilt generation after generation in slightly different spots. At Liang, researchers have reported all these ingredients in some form: charcoal, burned animal bones, localized ash-rich zones that might sound like case closed. Small humans, small cave, signs of burning. Of course they had campfires. Except caves complicate everything. Caves are like giant mouths open to the landscape. Water flows in, sediments wash down, bats roost and defecate. Roots penetrate from above. Fires lit outside the entrance can blow smoke and ash inside. Natural wildfires on the surrounding hillsides can sprinkle charcoal into open cracks and drip points. Over tens of thousands of years, a cave floor is more like a stirred stew than a neat layer cake. That means contamination is a constant worry. Charcoal from a much later fire can percolate down through fine cracks and end up in older sediments. Burrowing animals can disturb and mix layers. Even modern human activity, torches, campfires, excavation itself, can introduce burned material. So when someone says, "We found charcoal in the Hobbit layers," the next questions are immediate. Is it really in primary position? Is it sitting in a clear, undisturbed hearth? Or is it just isolated flecks in a matrix that's been churned by water and roots? Are the burned bones broken and cut in ways that match butchery? Or could they be random casualties of a forest fire? Different teams have answered those questions differently. Some researchers argue that the distribution of burned bones and charcoal at Liang is patchy and hard to tie to well-defined hearth structures. They suggest we might be looking at a mixture of natural fires outside the cave, occasional opportunistic use of embers, and later human activity, rather than a long tradition of controlled indoor fires by hobbits themselves. Others counter that the association between cut-marked Stegodon bones, stone tools and burned fragments in specific layers strongly points to active use of fire for cooking. In this view, the lack of textbook-perfect hearth circles doesn't matter. Small, repeatedly cleaned fires on a cave floor don't always leave dramatic archaeological features, especially in a wet tropical environment where ash dissolves and sediments slump. And there's a middle position, perhaps Homo floresiensis used fire, but irregularly. Maybe they didn't maintain permanent hearths, but grabbed natural fires when they appeared, lightning strikes, lava flows, brush burns, then kept embers going for days or weeks before losing them again. That's a very different lifestyle from, say, later Homo sapiens who treat fire as a constant managed presence. Why does it matter so much? Because sustained access to fire rewires the entire way a small-bodied hominin lives. Cooked food is easier to chew and digest. Heat breaks down collagen in meat and many plant toxins in roots and seeds. For a 3-foot hominin with a small gut but a demanding brain. Fire-assisted cooking can mean more calories extracted per hour of work, less wear on teeth, and shorter feeding times. That in turn frees up daylight for other tasks: tool-making, childcare, social bonding. Fire also changes your relationship with danger. Liang is not some cosy hobbit hole in an English hillside. It's a big cavern in a landscape with carnivores, giant storks, and Komodo dragons. A group with reliable fire can push predators back from the cave mouth, sleep deeper, and extend their awake time into the dusk and early night. Shadows on the wall become extensions of the day, time to fix tools, tell stories, plan hunts. Night activity is especially intriguing. If these small humans regularly lit fires inside the cave, they had to manage smoke, sparks, and the risk of asphyxiation. That implies knowledge of airflow, where in the cave to place a fire, how big to make it, when to let it die down. If instead they mostly used fires near the entrance or outside, their evenings would look different, more vulnerability, more dependence on the natural light cycle. Fire also sits at the crossroads of technology and social life. Even a simple campfire is a collective project. Someone gathers wood and kindling, someone guards the embers, someone teaches the next generation not to step into the coals. If they knew how to make fire from scratch, rubbing wood, striking stones, those techniques require fine motor skills, patience, and teaching. The ability to share fire between groups becomes a form of alliance. Visit your cousins, bring a burning brand, renew ties. So when we argue about fire at Liang, we're not just quibbling over ash stains. We're asking, were these island hominins living in a world shaped by controlled combustion, cooked Stegodon ribs, smoke-scented hair, evening conversations around glowing coals? Or were they closer to a pre-fire existence, with rawer diets, shorter days, and only occasional flirtations with flame? Right now, the evidence leans towards some use of fire by the makers of the Liang tools and butchery marks. But how regular, how skilled, how socially embedded that fire was, that's still under debate. What's clear is that whatever glow they had, it was enough to support a life lived partly in and around that cave. A life of cutting, cracking, and likely at least sometimes cooking. And once you imagine a fire-lit cavern, a question follows naturally. What were they doing with all that meat and bone out there on Flores? In the next section, we'll step out of the cave and into the hunt, following hobbits, stone flakes in hand, as they face miniature elephants, giant rats, and predators that definitely did not fear the dark. Step outside Liang, and the island does not feel like a tiny, gentle place. Flores in the Pleistocene was a closed experiment. No big mainland herds wandering in and out, no constant reshuffling of predators and prey. Once the sea rose around it, whatever made it to Flores was stuck there. Over hundreds of thousands of years, that isolation twisted the food web into something that looks familiar at first glance, and then very wrong. The centerpiece, at least from a hobbit's point of view, was Stegodon floresiensis insularis. Imagine an elephant, but shrunk by island life to about the size of a cow, maybe a bit bigger. Still several hundred kilos of meat, bone, fat, and hide. For 3-foot hunters with stone flakes, that's the jackpot animal. Stegodon bones litter the deposits at Liang and other Flores sites. They're broken, burned in some cases, and often found side by side with stone tools. Some of those bones carry cut marks, thin, V-shaped grooves exactly where you'd expect if someone was slicing meat off limbs, disarticulating joints or stripping tendons. That pattern is our first big clue. Cut marks that undercut tooth marks suggest primary access, hobbits there first, carnivores later. Tooth marks on top of cut marks suggest the opposite. At Liang, you see plenty of evidence that whoever used that cave had early access to at least some Stegodon carcasses. Whether that means full-on hunting or very aggressive scavenging is where the fight begins. On the hunting side, one scenario runs like this. Island dwarf elephants, like many island animals, gradually lost their fear of predators. With no packs of big cats, no hyenas, no ancestral wolves, the main threat on Flores might have been sporadic, ambush-based predators. That kind of environment selects for a certain laziness about danger. You can stand in the open a bit longer. You can linger at a waterhole, drop in a cooperative primate with tools and a plan, and naive megafauna become incredibly vulnerable. Stegodon were big enough that a lone hobbit with a stone flake was not bringing one down. But a group, one that understood the terrain, the escape routes, the soft spots. They wouldn't need super spears or perfect throws. They could drive animals into boggy ground, off small ledges, or into dead-end gullies. Once a Stegodon was stuck or injured, stone tools, persistence, and time could finish the job. That picture implies coordination, individuals taking different positions, anticipating where the animal will run, maybe even rehearsing simple roles. Some researchers look at the scale of bone accumulations and think that's exactly what we're seeing: repeated, organised access to large animals, not random pickups of an occasional carcass. But we have to be careful not to project a full Neanderthal-style hunting culture onto every pile of bones. An alternative is that hobbits were excellent opportunists, not specialised big game hunters. On an island with limited carnivores, a dead or dying Stegodon might sit untouched long enough for a small group of hominins to arrive, cut off choice bits, and retreat before the real dangers showed up. A flash flood, a fall, disease, or a stuck foot in mud could create a feast without any heroic hunting at all. The stone tools themselves don't settle the argument. They're simple flakes and chopping tools perfectly capable of butchering large animals, but not the kind of specialised, standardised spear points that scream projectile hunting. You can imagine both scenarios: coordinated drives without advanced weapons, or systematic scavenging that still yields primary access to meat. While the elephant analogue dominates the conversation, Flores offered other food sources with very different risk-reward profiles. There were giant rats, really giant. Some species on Flores reached the size of a small cat or even a rabbit. For a hobbit, that's an energy-dense, fast-breeding, relatively catchable bundle of protein. Many archaeologists think these rodents were a staple. Trap them, club them, grab them out of burrows, roast them if you have fire. If you look at later cave levels on Flores, you often find masses of rodent bones that may reflect exactly that kind of small game economy. Giant stalks loomed over the landscape as well. They were tall, carnivorous, and probably willing to feed on hobbit-sized bodies given the chance. But large birds also leave eggs, fledglings, and scavengable leftovers. It's possible that these eerie neighbours were both a danger and an occasional resource, though direct evidence for hobbits eating birds is thinner than for Stegodon and rats. The truly dangerous celebrity in this ecosystem, though, is the Komodo dragon. Today, these monitor lizards are apex predators and notorious scavengers, fully capable of killing a human. On Pleistocene Flores, close relatives or direct ancestors of Komodo dragons would have been even more central to the food web. They could smell blood from far away, claim carcasses, and ambush anything that lingered too long at a kill site. For a 3-foot hominin, that changes the entire calculus of hunting and scavenging. Bringing down a Stegodon, or just finding one dead, is only half the battle. The other half is how fast you can process the carcass and how effectively you can defend it. If you have fire, smoke and flame might buy you time. If you have numbers, a noisy stone-throwing mob might keep a dragon just far enough back for long enough. If you have neither, your best strategy might be speed. Strip the choicest parts, crack the big limb bones for marrow, and retreat to the safety of a cave or cliff before a dragon's tongue flickers into the scene. And Komodo dragons weren't the only hazard. The same cliffs and gullies that make great hunting traps for Stegodon are also perfect places to break an ankle or fall to your death. Caves shelter you, but they attract bats, snakes, and other animals. Tropical rivers hide crocodiles. The landscape itself is a predator of the unwary. In that context, cooperative behaviour becomes a survival tool, not a luxury. You don't need to assume elaborate social contracts or complex language to get basic teamwork. A few individuals shouting, gesturing, and following habitual patterns could coordinate a drive. Watch for dragons while others cut meat or help injured group members back to shelter. But how far that cooperation went, whether hunts were carefully planned, whether roles were taught and inherited, whether knowledge of the best ambush points was shared across generations or guarded by particular families, that's all inference. Bones and stones can tell us that meat was eaten, animals were processed, and risks were taken. They can't yet tell us whether the hobbits of Flores had hunting stories, taboos, or heroes. What the archaeological record does show is a small-bodied human species surviving for hundreds of thousands of years in a predator-rich, resource-limited island system. However they balanced hunting and scavenging, however they navigated naive prey and dangerous neighbours, they got enough right to persist far longer than our own species has been around. And that endurance raises another question. What kind of bodies and movement patterns let them pull that off? To answer that, we have to look down at feet, legs, and the strange way a hobbit might have walked across this lethal little island. If you met one of these people on a trail, the first thing you'd probably notice after the height is that something about their walk looks off. Not wrong, just different. We know that because their skeletons are, frankly, weird. The best preserved hobbit, LB1, has a foot that is long for her stature. Not clown shoe huge, but proportionally more like a small ape than a modern human. The toes are relatively long, the big toe is in line with the others, like ours, so she wasn't gripping branches with it like a chimp. But the midfoot, the middle of the arch, is built differently. The bones suggest a flatter, more flexible structure, and the joint shapes hint at a foot that didn't lock into the rigid lever modern humans rely on for long-distance, high-efficiency walking. Move up the leg, and the picture stays strange. The shin bone is short. The femur, the thigh bone, has angles at the knee and hip that don't match neatly with either early Homo erectus or us. The pelvis is wide relative to height. The shoulder and wrist look primitive in some ways, and the overall limb proportions are those of a small, slightly top-heavy walker with a low centre of gravity. Put those pieces together, and most researchers agree on one thing. A hobbit on Flores was not striding along the savannah like a marathon-ready Homo sapiens. Their gait was probably shorter-stepped, with more knee and hip flexion, and a foot that rolled through the ground, contact more softly and less spring-loaded. Think of a walk that wastes a bit more energy per metre, doesn't convert as much impact into forward motion, and maybe looks a bit like a compromise between a tree climber and a ground dweller. But here's where the story gets interesting. Less efficient in one environment can be good enough, or even better suited in another. On a small, rugged volcanic island, you don't need to jog 30 kilometres across open plains. You need to scramble up steep gullies, cross streams slick with algae, wedge yourself into caves, and navigate roots, boulders, and loose scree. A long, stiff, springy foot like ours is fantastic for flat ground. On uneven terrain, a slightly longer, more flexible foot with more surface area can actually help with balance and grip. A short, lower leg and low centre of gravity also makes sense when your daily life involves clambering over broken ground and ducking into tight spaces. That body plan is more stable on slopes, less likely to topple when a rock shifts, and better at absorbing sudden changes in footing. It might have helped them scramble up low cliffs or move quickly through dense brush, even if it cost them some speed and efficiency on a straight, clear path. Endurance is trickier. From a purely mechanical standpoint, short legs and a less modern gait mean higher energy costs per kilometre. A hobbit probably burned more calories going the same distance than you would. On a marginal island, where food can be scarce and droughts or volcanic episodes can strip the landscape, that sounds like a disadvantage. But daily range isn't just about efficiency, it's about scale. Flores is not a continent. If your typical foraging radius is, say, 3-5 kilometers from a home base, and you know every game trail, fig tree and waterhole in that circle, you don't need to be an ultramarathoner. You need to be thorough, cautious, and good at micronavigation. A body tuned for stability in climbing, even if it's not optimized for long, fast treks, can still meet those demands. There's also the possibility that what they lost in mechanical efficiency, they compensated for with behavior. Shorter daily ranges, more knowledge of local patches, more emphasis on predictable resources like rodents and plants, and careful timing of risky trips to Stegodon carcasses could all minimize the need for long, costly journeys. We should be honest about the limits here. Reconstructing movement from bones is a bit like reverse engineering choreography from a pile of disconnected joints. Shape doesn't translate perfectly into motion. Soft tissues, muscles, tendons, ligaments, fat don't fossilize. Two species with the same bone proportions can still move differently depending on muscle arrangement and neural control. So when scientists model Hobbit Gait, they're working with best guesses. Comparisons to modern humans, to apes, to earlier Homo fossils, plus computer simulations of joint ranges and load paths. What we can say with some confidence is that these people did walk upright, on two legs habitually. They weren't knuckle walking or swinging through trees as their main mode of travel. Their bones show the wear patterns of committed bipeds. Whatever quirks their stride had, it was good enough to move them between water sources, hunting spots, and shelter day after day, year after year, for an absurd span of time. And that's the real test. You don't survive on a dangerous island for hundreds of thousands of years with a catastrophically bad design. Their bodies, odd to our eyes, were tuned to a scale of movement that matched the island's size, the patchiness of its resources, and the risks of its predators. How they moved shaped how far they could range, how they chose routes, how often they shifted camp, and how tightly their social groups clustered around reliable refuges like Liang. Which leads naturally to another question. If their bodies were adapted this specifically to Flores, what kind of social world grew around those short legs and strange feet? If you want to know how a species thinks, you look at what it has to do to stay alive. On Flores, that meant something very simple and very unforgiving. Nobody survives alone. We'll never find a fossilized conversation. We don't have hobbit villages frozen in ash, or murals showing family life, or written records of who owed who a favour. Social life is one of the hardest things to reconstruct because it's made of behaviour, and behaviour mostly evaporates the moment it happens. But it never evaporates completely. It leaves fingerprints. Start with the basics. Liang wasn't a one-time crash pad. It was used again and again by multiple generations. You see repeated layers of occupation, stone tools accumulating, food remains piling up, ashes and debris in recognizable patterns. That's not a lone wanderer ducking into a cave during a storm. That's a place groups came back to, a home base or at least a regular seasonal camp. A shared base changes everything. If you're returning to the same shelter over and over, you're probably coordinating who goes where, who hunts, who gathers, and who stays behind. You can leave things there, stone blanks, half-finished tools, piles of firewood, and trust that other group members will use and maintain them. That implies expectations, habits, unspoken rules. In other words, a social system. Then there's the hunting problem. On Flores, the juiciest payoff was Stegodon. Even the pygmy version is not a snack you casually pick up on your own. Taking down or seriously scavenging from something that big, in a landscape that also holds giant storks and Komodo-scale predators, is a coordination project. You need multiple individuals moving in concert, some driving or distracting the animal, others flanking, others ready to butcher quickly before something big and toothy shows up. Even if they were mostly scavenging natural deaths or predator kills, getting in, stripping meat, and hauling it back to Liang demands timing and division of labour. Coordinated tool use is the quiet clue here. The stone tools at Liang are simple in design, but they're standardised. The same basic forms produced over and over in different layers for thousands of years. That suggests shared know-how, not individual improvisation. Somebody figured out the Liang way of making a cutting edge, and that recipe got passed around and passed down. To keep a technical tradition stable across centuries, you need more than copying by accident. You need teaching, demonstration, correction, some form of do it like this, not like that. That doesn't automatically mean full-blown language with grammar and stories and jokes, but it does push us into the territory of structured communication, sequences of sounds or gestures that carry specific, repeatable information, where the good stone is, how to strike it, when to retreat from the Stegodon carcass. Could they have had something language-like? Possibly. Other social mammals already give us the lower bound. Meerkats with distinct alarm calls for aerial versus ground predators. Monkeys with calls that function almost like eagle, leopard, snake, add a bigger brain, longer childhoods, and a life that depends on complex foraging. And it becomes hard to imagine Flores hobbits communicating only in grunts and random noises. But hard to imagine is not data. We don't have their throats, their tongues, or their auditory brains. The safest thing we can say is this: their way of life would have strongly rewarded any improvement in precise, flexible communication, whether that took the form of a rich spoken language as we'd recognize it, or a simpler mix of vocal calls, facial expression, and gesture. We just don't know. Where the bones get a little louder is in the question of care. LB1, the famous skeleton, wasn't just small. She had skeletal quirks that might have affected mobility and health. Other hominin fossils from elsewhere show individuals who lived for years with serious injuries, healed fractures, or birth defects. Every time we see that, the same lesson pops up. Someone must have helped them. An individual who can't walk far, or can't hunt, or can't reliably feed themselves doesn't make it to adulthood without others stepping in. On a small island, the cost of carrying non-productive members is high. Food is limited. Droughts happen. Predators don't care that you're being compassionate. So if a population repeatedly chooses to support injured or impaired individuals, there has to be a payoff. One payoff is experience. Older group members, even if physically weaker, can remember where water held out in the last dry season, which valley floods, which plant is edible only after cooking. Another payoff is childcare. A grandmother or uncle who can't chase Stegodon might still watch the kids, freeing up prime hunters and foragers. Caregiving and social support in this view are not just niceness, they're adaptations. Groups that keep their knowledge holders and babysitters alive do better over centuries than groups that abandon them. So the most reasonable model for Hobbit society is not a harsh world of hyper-individualistic foragers, each out for themselves. It's small, tightly knit groups, probably related, sharing shelter, dividing labour, teaching skills and caring, at least sometimes, for the weak. Notice what we're doing here. We're building a picture out of indirect evidence. Cave reuse, tool traditions, the demands of hunting, the basic economics of survival on an island. These are plausible models, not direct snapshots. We don't know how many individuals shared Liang at once. We don't know their marriage rules, their conflicts, their songs. We're stacking probabilities, not certainties. But even that probabilistic picture matters because it sets the stage for the bigger mystery. A small, cooperative, reasonably well-adapted species with shared tools, shared spaces, and likely shared knowledge manages to hang on in this tricky environment not for a few thousand years, but for something like 700,000. To understand how they could last that long, and how they could then vanish so abruptly, we need to zoom out from daily life to deep time. What does 700,000 years really mean for a species marooned on an island? 700,000 years sounds like a big round number on a museum sign. It doesn't feel real, so let's make it real. If we're right that some kind of small-bodied human lineage was on Flores from about 1 million years ago, and that Hobbit-like beings were still there 50,000 years ago, we're not talking about one unbroken village that lasted through all that time. We're talking about a pattern, waves of occupation, abandonment, and reoccupation stretched across ice ages and sea level changes and volcanic episodes. In archaeology, they survived 700,000 years really means whenever we zoom in on this island at different moments across that span, we keep finding the fingerprints of hominins. The deepest fingerprints are not bones at all, they're stone. At a site called Mata Meng, and at a few other localities on Flores, archaeologists have found stone tools locked in layers that date back to around 1 million years ago. Simple flakes, crude cores, nothing fancy, but they're unmistakably shaped by human hands, or at least human-like hands. Fast forward hundreds of thousands of years, and at Liang you find another stone toolkit. Different context, different time, but again, deliberate flaking, repeated forms, clear evidence that some hominin knew how to turn rock into cutting edges. That's the backbone of the long survival story. You have tools at the bottom of the time column, you have tools close to the top, and you assume that for most of the time in between there were people of some kind living and dying on Flores. But that assumption only works if the story across those layers hangs together. Here's how scientists actually build that story. First, they line up the clocks. Different sites use different dating methods. Argon dating on volcanic ash, uranium series on cave formations, radiocarbon for the youngest material, even electron spins locked in grains of quartz and feldspar. Each method has its own error bars, its own ways of failing. When several independent methods point to similar ages for different layers, confidence goes up. Then they look sideways as well as down, horizontal comparisons. Is the layer with tools at one valley the same age as the layer with tools at another valley? Does a particular volcanic ash, the same chemical fingerprint, the same eruption, show up at both, letting you tie their timelines together? Can you trace a distinctive soil horizon or a climate shift across multiple sites? When those lines start to cross, you can sketch a rough island-wide map. At this time, hominins are here and here. At that later time, they show up over there as well. It's not just human traces they follow, it's the whole environment. Fossil faunas, Stegodon teeth, giant rat bones, Komodo ancestors tell you what kind of ecosystems surrounded your hominins. Pollen grains buried in mud layers reveal which plants dominated. Open grasslands, dense forest, something in between. Oxygen isotopes from cave deposits and ocean cores record global and regional climate swings. Put together, you get a moving backdrop. Sea level drops during ice ages, perhaps exposing more stepping stone islands. Sea level rises, isolating Flores again. Forests expand and contract. Rivers shift. Volcanic eruptions blanket parts of the island in ash. The key question then becomes, through how many of these environmental mood swings do we still see hominin activity? If the answer is almost all of them, you're looking at real continuity. a lineage that rides out change after change, adapting in place? If the answer is short bursts with long empty gaps, then the story might be one of repeated colonization and extinction, floras being repopulated again and again by new arrivals. For true continuity over hundreds of thousands of years, several things would have to be true. Hominins on Flores would need to be resilient to big climate oscillations, shifting their foraging strategies as forests turn to grasslands and back again. They'd need enough population spread, think those scattered bands we talked about, that no single event could wipe them out entirely. They'd probably need some way of moving across the island, and maybe on and off it when sea levels and coastlines changed. And crucially, when you compare tools through time, you'd expect some kind of thread. The details can change, techniques can be lost or reinvented, but you're looking for an underlying accent in how stone is worked, similar ways of striking flakes, similar choices of raw material, similar shapes that show up again and again. On Flores, that thread is there, but it's thin. The oldest tools are simple. The Liang tools, much later, are also simple. They resemble each other in broad strokes, but not so uniquely that you can say with absolute confidence. Same cultural tradition, just much older. That's why some researchers argue for deep continuity. An early colonist population shrinks and shrinks until you get Hobbit-sized descendants, who then hang on in modified form for hundreds of thousands of years. Others leave more room for replacement. Perhaps an early hominin arrives and disappears, and a second wave, already small-bodied or quickly dwarfed, colonizes the island later. Right now, the 700,000-year survival is best seen as a synthesis, not a single smoking gun. You take the million-year-old tools, you take the Hobbit bones and tools from Liang. You link them with island geology, sea level history, and the biology of insular dwarfism, which usually requires long spans of isolation. You add in the lack of evidence for any big intervening hominin arrival on Flores, and you get a picture that favours continuity, one lineage, or at least one continuous presence, stretching across almost 750,000 years. But every piece of that picture has caveats. The dating has uncertainties. The tools are generic enough that convergent simplicity is possible. The fossil record is so sparse that entire episodes of colonization and extinction could have come and gone without leaving a single skull. What 700,000 years really represents, then, is not a boast about precision. It's a statement about scale. Whoever the Flores hobbits were, they weren't a brief experiment. They were part of the island's story across deep time, long enough for climates to flip, animals to shrink and grow, coastlines to move hundreds of kilometers. And that's exactly what makes the ending so jarring. A lineage that seems to be woven into the island for geological ages vanishes, in archaeological terms, almost between one layer and the next. To make sense of that, we have to turn from the slow grind of deep time to the sharp edges of catastrophe. So what does vanished overnight actually look like when you're staring at dirt? In archaeology, an abrupt disappearance isn't a dramatic movie cut. It's a pattern in layers and numbers. At Liang, you have strata where hobbit bones and their simple stone tools appear together with the island's old fauna, pygmy Stegodon, giant rats, certain birds and reptiles. Those layers get dated using radiocarbon for the youngest bits, luminescence for the sediments, uranium series and argon methods for volcanic material. You get a cluster of ages, call that the Hobbit horizon. Then, above that horizon, you hit layers that are younger, tens of thousands of years younger. The dates march forward in time, but in those younger layers, the Hobbit bones are gone. The Stegodon is gone, the toolkits change. Eventually you start seeing modern human signatures, different lithic styles, sometimes different fauna, and much later, actual Homo sapiens remains. If you can trace many of those lines, dates, fauna, artifact, smoothly upward without obvious breaks in sedimentation, and the Hobbit package still drops out. That's what archaeologists call an abrupt disappearance. It's not that time stops, it's that one component of the system blinks out while the rest keeps recording. But here's the catch, the record we're using to say this is painfully thin. There's a huge difference between nobody lived here and we haven't yet found evidence that anybody lived here. Flores is mountainous, heavily vegetated, riddled with caves that haven't been touched. The few sites we have are tiny pinpricks in a large, complicated landscape. When we say the hobbits vanish around 50,000 years ago, what we're really saying is above a certain dated level at one cave, and so far at a handful of other spots, our specific combination of hobbit bones and associated fauna doesn't appear. That might be evidence of absence, or it might just be absence of evidence. Sampling bias is brutal in paleoanthropology. Skeletons only fossilize under special conditions. Stone tools only preserve where they were dropped, buried, and not eroded away. Even then, we only see what we happen to dig. Now imagine a species that probably never numbered more than a few thousand individuals on the entire island at any one time. Maybe far less. Each small band might leave behind a scattering of stone flakes, a handful of butchered bones, a few hearths. Over tens of thousands of years, that adds up. But spread across an island, filtered by erosion and sedimentation, and later disturbance, most of those traces will be erased, buried deep, or simply never intersect with the narrow trenches archaeologists have opened. Small populations leave faint archaeological signatures even when they're doing just fine. Drop their numbers further through a bad climate swing, a disease episode, competition with a newcomer, and their footprint shrinks almost to nothing long before the last individual dies. For a while, the species is biologically alive but archaeologically invisible. Then both lines end, and all we see from our distant vantage point is a fade-out that looks suspiciously like a cliff. So when we talk about the hobbits vanishing overnight, we're compressing several different possibilities into one dramatic phrase. They might have disappeared quickly in real time, wiped out over a few generations by some catastrophic eruption, a runaway epidemic, or rapid ecological collapse. In stratigraphy, that could look like one layer full of them and the next one empty. They might also have dwindled slowly over thousands of years, their range shrinking into remote refuges, their numbers bleeding away as conditions worsened or competitors arrived. That kind of drawn-out decline can still look like a sudden break if the only site we have just happens to lie outside their final tiny strongholds. Either way, the archaeological gap tells us two things with some confidence. First, whatever hominin population produced the Liang hobbits and their toolkit is no longer detectable on Flores after a certain point. Second, other things, different faunas, different technologies, later modern humans do show up in those younger layers. The record doesn't go blank. The cast changes. That's our starting gun for extinction hypotheses. If a lineage that appears stable across deep time suddenly drops out of a continuous sequence, something changed. The obvious candidates line up in four broad categories. Environmental pressure, long-term climate shifts, habitat change, or resource depletion that gradually undercut their survival. Catastrophe, volcanic eruptions, tsunamis, landslides, or sudden climate shocks that hit fast and hard. Competition, new arrivals, most likely Homo sapiens, outcompeting them for prey, taking over key habitats, or indirectly causing their decline. Disease, pathogens introduced by animals, other humans, or environmental changes to which small inbred populations are especially vulnerable. To make progress, we need criteria, questions we can actually test against the layers and the bones. Do we see a sharp change in the environment right at or just before the Hobbit horizon ends, shifts in pollen, faunal turnover, big ash layers, erosion surfaces, that points toward climate or catastrophe. Do the youngest Hobbit-bearing layers overlap in time with evidence for modern humans on Flores or nearby islands? That's key for competition scenarios. Is there a pattern of gradual faunal decline, shrinking body sizes, or stressed individuals in the last Hobbit levels that might signal slow environmental squeeze or chronic disease? And finally, is the gap truly island-wide or just local to Liang? Finding younger Hobbit traces elsewhere on Flores would radically rewrite the ending. In the next sections, we're going to walk through each of the big suspects: environment, catastrophe, competition, and disease, and see how they stack up against those criteria. Because buried in that thin, fragmentary record is a simple question with a surprisingly hard answer. How do you kill a species that has already survived almost everything? Flores does not sit in a gentle neighbourhood. Zoom out on a tectonic map, and the island lies right along the collision zone where the Australian plate is diving under the Sunder plate. That subduction line is like a zipper of volcanoes running across Indonesia. Flores is threaded onto that arc. Steep stratovolcanoes, active faults, a history written in lava and ash. On a place like this, normal life already includes earthquakes, minor eruptions, and periodic ash falls. Forests regrow. Rivers cut new paths. Animals shift their ranges. A resilient ecosystem and a resilient species can absorb a lot of that. Every so often, though, a volcano stops playing by the usual rules. Instead of a local nuisance eruption, you get something bigger. A major explosive event that dumps meters of ash across whole valleys, chokes rivers, strips vegetation, kills or drives off much of the large fauna. In island settings, those events are especially brutal because there's nowhere else to run. You can't just march 100 kilometers inland and find unaffected habitat. You're ring-fenced by water for tiny-bodied, small-brained hominins living at very low population densities. This is where catastrophe stops being an abstract category and turns into a real extinction mechanism. There are a few ways a big eruption could break a system like the one the Hobbits depended on. First, simple habitat loss. If your core foraging territory is a mosaic of forest, scrub, and open patches around a cave like Liang, and that whole patchwork gets buried in ash, you lose your pantry. Plants wither under abrasive, sun-blocking dust. Leaf surfaces clog. Seed crops fail. Insects and small vertebrates drop in numbers. The pygmy stegodons you rely on for meat and marrow are either dead, pushed into safer refuges, or too nutritionally stressed to hunt. Second, food chain collapse. Ash doesn't just smother, it infiltrates. Grazers inhale it while feeding, abrading lungs and guts. Herbivores find less to eat and start dying off. Predators and scavengers, giant storks, Komodo dragons, hominins, ride out a brief feast of carcasses followed by a long famine. If your diet and technology are already marginal, your buffer against that shock is thin. Third, direct physiological stress. Fine volcanic ash is brutal on lungs and eyes. Even relatively small ash falls can cause respiratory distress, especially for children, the elderly, and individuals with pre-existing weaknesses. In a population that may already be inbred and small, losing a few key adults, a master hunter, an expert firekeeper, a midwife can tip a band from barely sustainable to non-viable. Catastrophe doesn't have to be a single apocalyptic blast. A sequence of medium-sized eruptions over a few centuries could be just as lethal, constantly knocking back vegetation before it recovers, keeping herbivore numbers low, and forcing human groups into ever smaller refuges. So, can we actually see any of this in the rocks? Across Flores and neighbouring islands there are thick tephra layers, hardened ash from multiple Pleistocene eruptions. Some are local from Flores volcanoes, Others may be fallout from bigger regional events. One of the most famous giants is Toba, a supervolcano in Sumatra that erupted massively around 74,000 years ago. Its ash blanket shows up across South Asia and into the Indian Ocean. If you're trying to link catastrophe to Hobbit extinction, you look for patterns like this: Hobbit bones and tools up to a certain depth, then a big ash layer, then no more hobbits above it. If you can date that ash using argon or other radiometric methods, and it lines up with the disappearance window, the story starts to look compelling. Some researchers have suggested exactly that kind of sequence for Flores: local volcanic activity ramping up in the late Pleistocene, stratigraphic packages where major ash falls bracket changes in fauna. In a neat narrative, the last Hobbit horizons would sit just below one of those volcanic bookmarks. The reality, as usual, is messier. The dating uncertainties on both the Hobbit layers and the ash beds are still big enough that around 50,000 years ago can stretch by several thousand years in either direction. Different dating methods can disagree. Erosion and later disturbance can blur contacts between layers that once were sharp. A thick ash bed that looks like a single giant event may, under close inspection, turn out to be multiple eruptions smeared together. Regional records don't simplify things either. Yes, there's evidence for significant volcanic activity in Indonesia in the broad window when hobbits disappear. But tying a regional signal, like Toba, to the specific ecology of Flores, and then to a particular valley or cave, is a long chain of inference. Even if the timing matched perfectly, catastrophe as a sole explanation runs into another problem: selectivity. In the Liang sequence, the hobbits and Stegodon vanish, but other elements of the fauna carry on. Some species disappear, others persist, still others appear later. That's what you'd expect after a big ecological shock: winners, losers, and opportunists. But the question becomes, why would a catastrophe remove this particular hominin lineage completely, while leaving enough ecological structure for later humans, modern Homo sapiens, to thrive on the same island? If the eruption was so severe it wiped out every hobbit on Flores, how did anything larger than a rat survive? If it was patchy enough to leave Komodo dragons and other predators in business, why didn't at least a few hobbit bands hang on in refuges and later repopulate, the way human groups did after countless disasters elsewhere? This is where population dynamics bite. A volcanic catastrophe doesn't have to kill every last individual to cause extinction. It just has to knock numbers below a threshold where recovery is realistic. Imagine a species already living close to the edge. Maybe a few hundred breeding adults spread across the island in scattered groups. Now hit them with a shock that halves their numbers, squeezes them into a handful of marginal refuges, and scrambles their traditional migration and mating routes. What's left afterward isn't just fewer people, it's fewer social networks, fewer potential partners, fewer specialists, less cultural knowledge. Inbreeding rises, random bad luck hits harder. A couple of bad seasons, one disease outbreak, a landslide in the wrong valley, and what looked like a post-eruption survival can quietly tip into a tailspin. In that sense, catastrophe is often the trigger, not the whole story. Its strengths as an explanation are obvious. Flores is volcanic, ash and tephra are physically there, and ecological shocks are known extinction drivers on islands. A big eruption fits the relatively abrupt archaeological disappearance far better than a slow, erosion-driven stratigraphic illusion. The weaknesses are just as important. The dating is still fuzzy. The impact of specific eruptions on Flores' interior habitats is poorly constrained. And we don't yet see a clean, island-wide pattern of hobbits below, ash, nothing above that would let us confidently blame a single event. More likely, if volcanoes played a role, it was as part of a cascade, ash-driven habitat loss and food stress pushing already vulnerable hobbit populations into smaller, more fragile enclaves. Into that unstable system something else could easily arrive or emerge to finish the job. And that brings us to the other prime suspect waiting just off stage, us. When you're reconstructing an extinction, timing is everything. We know hobbits disappear from Liang somewhere around 50,000 years ago. We also know that modern humans, Homo sapiens, show up across Southeast Asia and into Australia not very long after. The question is whether those two timelines simply rhyme or actually overlap. The broader regional picture is fairly clear. Stone tools and other traces put Homo sapiens in mainland Southeast Asia by at least 70,000–60,000 years ago. By 45,000 years ago, they're in Australia. You don't get from Africa to Australia without crossing Wallessa, the island chain that includes Flores. So at some point in that window, our kind is moving through this region, skirting or hopping across deep water channels, exploring coastlines and islands. Flores is right there, a stepping stone on one of the plausible routes south. Inside Liang, though the story looks staggered. Hobbit bones vanish. Their associated crude stone tools taper off. Then, in layers above, separated by time and sediment, you start to see something different, more modern stone tool technology, different patterns of occupation, evidence that later humans used the cave. The uneasy part is the gap. Depending on which dating model you use, there may be several thousand years between the last clear hobbit remains and the first clear Homo sapiens traces. That gap is big enough that you can't point to a single layer and say, here is where they met. It's also small enough that, in evolutionary terms, it's basically the same moment. So did we actually meet them? There are three broad possibilities. 1. No overlap. Hobbits go extinct for reasons of their own. Volcanic cascades, climate shifts, internal population collapse, and only later do our ancestors arrive to find an empty island with a few strange bones in the cave. In that scenario, we're scavengers of a mystery, not culprits. 2. Brief, local overlap that leaves almost no clear trace. Hobbit bands hanging on in dwindling numbers in a few valleys, while Homo sapiens coastal foragers begin probing the island's edges. Maybe a few cautious encounters, some distant sightings, a shared waterhole or carcass, then a slow fading out of the smaller, rarer population. 3. More substantial overlap and direct interaction, competition, displacement, maybe even predation, but the physical evidence of that interaction hasn't been captured in the small fraction of the island we've excavated. The last idea is the most dramatic, so it gets the most attention. We know from Europe and Western Asia that when Homo sapiens expanded into territories held by Neanderthals, the Neanderthals disappeared within a few thousand years. In Siberia and East Asia, Denisovans seem to fade out after modern humans arrive. In North Africa, older Homo lineages vanish as our form takes over. In every case, the exact mechanisms are debated. Was it violent conflict? Subtle ecological competition, disease, cultural takeover? Probably some combination, varying from place to place. But the pattern repeats. Wherever we show up, other human species eventually don't. So it's tempting to look at Flores and say, well, we did it again. We had advantages that matter enormously on an island with limited resources. Our technology was more flexible. Sapiens arriving in Wallacea were likely already using complex projectiles, sophisticated fire management, maybe even early watercraft and nets. That kind of toolkit lets you tap into new food sources, fish, shellfish, birds, offshore reefs, that a small ground-bound hunter like Homo floresiensis might not exploit efficiently. Our social networks were larger and more structured. Modern humans travelled in groups that were not just bigger but more tightly interlinked across distance. Information, marriage partners, and innovations could flow between bands. On an island hit by eruptions and climate swings, that social web acts like a shock absorber. We may also have carried something even more lethal than spears, pathogens. A disease that produces mild symptoms in a large, genetically diverse sapiens population can rip through a tiny inbred group with devastating effect. You don't need warfare if contact alone, sharing water sources, scavenging the same carcass, transmits something new. Finally, there's the raw arithmetic of competition. Two human species hunting the same stegodons, gathering the same fruits, occupying the same caves is not a stable long-term configuration on a small island. The one with the broader diet, better tools, deeper coalitions, and faster cultural learning tends to win, even without consciously trying to exterminate the other. So why don't we see clearer fingerprints of that process at Liang? No unmistakable sapiens spear points lodged in Hobbit bones, no shared living floor littered with both species' tools. Partly it's sampling. Liang is one cave in one valley on one side of the island. If hobbits and sapiens overlapped only briefly or mostly in other areas, coastal cliffs now submerged by rising seas, smaller shelters never excavated, we might simply have missed the key sites. Partly it's preservation. Bones don't always survive. Surfaces get eroded, trampled, dissolved. A healed injury from a thrown spear looks a lot like a break from a rockfall once it's fossilized and fragmentary. Even cut marks can be hard to distinguish from carnivore tooth scrapes or natural abrasion. And partly the overlap may have been more ecological than theatrical. Imagine Homo sapiens groups establishing camps near rich coastal estuaries, intensively harvesting shellfish, fish, and small game, burning back vegetation to encourage certain plants. Over decades they change fire regimes, prey pressure, and landscape structure. Inland hobbit groups already hammered by eruptions find their remaining foraging zones shrinking, key prey species failing to rebound, and safe travel routes disrupted. No battlefield, no massacre, just a slow tightening of the ecological noose. When we look for analogies, the Neanderthal case is the obvious comparison, but it should be handled cautiously. Neanderthals were close to us in brain size and tool sophistication. Hobbits were much more anatomically and technologically distinct. That might make them easier to outcompete, or it might mean they occupied slightly different niches, allowing longer coexistence. There are also differences in scale. Europe is a vast landmass with many refuges. Flores is not. A lineage that might have survived for tens of thousands of years in scattered mountain pockets on a continent could be snuffed out far faster on an island once its numbers dip. All of this uncertainty is why the "we killed them" narrative, while emotionally satisfying, is still just one hypothesis among several. We're very likely part of the story of Hobbit extinction. Whether we're the final shove off the cliff or just another weight added to an already overloaded system remains unresolved. By the way, if puzzles like this fascinate you, the kind where the evidence is just good enough to frame the mystery, but not quite good enough to solve it, I've put together a book on 12 unexplained cases like this from across prehistory and history. You can find it on the website. There's a link in the description. And for this week, there's a discount running if you want to dive deeper into the weird edges of what we know. On Flores, the bottom line is this: the arrival of Homo sapiens and the disappearance of Homo floresiensis happen in the same narrow slice of time, in the same small piece of the world. Volcanoes and climate may have pushed the hobbits to the brink, but we may have been the factor that made recovery impossible. To prove that, though, we need more than timing. We need contact. And that means new caves, new sites, and one holy grail piece of evidence that could rewrite the entire story. If you wanted a single piece of evidence that would blow this case wide open, it would be DNA from a hobbit. Not just because it would be cool to read the genome of a 3-foot human from a remote island, but because it would settle several fights at once. Where they sit on the human family tree. How inbred their population really was. Whether they carry traces of Denisovan-like ancestry, even whether they were exchanging genes with anyone else late in their history. The problem is Flores is just about the worst place on Earth for ancient DNA. DNA is fragile. It breaks down with heat, humidity, and microbial activity. In cold, dry caves in Siberia, you can pull readable DNA out of bones more than 100,000 years old. In a warm, wet, tropical cave like Liang, you're lucky if anything survives for tens of thousands of years. And even then, it's usually in miserable condition. The hobbit bones we have been cooked, soaked, and chemically abused by the tropical environment for tens of thousands of years. So far, attempts to extract DNA have come up empty or ambiguous. That might change with future techniques, methods keep improving, but nobody in the field is betting the whole mystery on perfect hobbit genomes falling into our laps. So researchers have turned to more durable molecules. One alternative is ancient proteins. Certain proteins in bones and teeth survive far longer than DNA and still carry evolutionary information. By comparing their amino acid sequences across species, you can infer relationships, a bit like doing family history with a handful of phrases instead of an entire library. Another is microwear and residue analysis. By looking at microscopic scratches on hobbit teeth, or tiny wear patterns on stone tools, you can infer diet and behaviour, what they were chewing, how they used their tools, whether there were changes over time that might signal stress or adaptation. Then there are sediments themselves. Cave dirt is no longer just background. It can preserve fragments of DNA and proteins from whatever lived and died there, plus traces of ancient fire, pollen and dung. Even if the hobbit bones won't talk, the mud around them might. But molecules on their own won't be enough. We also need more bodies. Right now, our picture of Homo floresiensis is built on a small sample, mainly one fairly complete skeleton and scattered bits from a handful of other individuals. That's like trying to reconstruct an entire language from one half-burned book and a few torn pages. What would help? More individuals for a start, children, adolescents, older adults, males and females. If we had a decent sample of hobbits from different ages and both sexes, we could separate what's normal variation from what's genuinely distinctive. Did they all share the same odd proportions? Were there growth disruptions that point to chronic stress near the end of their history? We also need better contexts. Hobbit bones and tools found in clear, undisturbed layers, with associated animal remains and datable materials, would let us reconstruct specific moments. A hunting camp after a Stegodon kill, a shelter used only seasonally, a burial site versus a carnivore den. Each of those scenarios tells you something different about behavior, cognition, and vulnerability. Crucially, we need more sites, not just more finds from Liang. Flores is riddled with caves and rock shelters that have never been surveyed, let alone excavated. Most of our story comes from one cave in one valley. That's like trying to understand all of Neanderthal Europe from a single rock shelf in France. Systematic surveys, walking valleys, scanning cliffs, mapping sinkholes, could turn up new hobbit sites from different time periods. Early sites closer to 700,000 years ago would clarify how the lineage started. Late sites closer to 50,000 years ago, especially outside Liang, could reveal whether they were hanging on in scattered refuges or already gone before the big eruptions and our arrival. And some of the best sites might be underwater. Sea levels during most of Hobbit history were much lower than today. Coastal caves, shorelines and estuaries they used are now drowned. Underwater archaeology in Wallacea is still in its infancy. But as techniques improve, we may start finding submerged rock shelters, beach middens, or even kill sites that preserve a chapter of the story we're currently missing: how hobbits, and later Homo sapiens, used the coasts. All of this has to be tied together by better dating. Right now, part of the confusion around Hobbit extinction is simply that the error bars are big. Different dating methods on different materials sometimes yield slightly different answers. Improve the precision and the number of dates on volcanic layers, on cave sediments, on animal bones, and you suddenly see whether gaps are real or just artifacts. Maybe the extinction gap between hobbits and sapiens collapses to almost nothing. Maybe it stretches, making human-hobbit overlap unlikely. Either way, sharper timelines force theories to sharpen with them. And as we gather all this new evidence, the bigger picture of human evolution keeps shifting under our feet. 20 years ago, a 3-foot human on Flores with a tiny brain looked almost impossible within the neat, linear story many people told about human evolution. Brains get bigger, bodies get taller, technology more complex. End of narrative. Since then, the discovery of Denisovans, new species like Homo luzonensis in the Philippines, and older, unexpectedly complex Homo sapiens fossils in Africa have all blown holes in that straight line. We now see our past as a tangled bush of experiments, side branches, and local adaptations. Flores sits inside that new picture very differently. If our lineage was full of small-brained, island-adapted, locally successful humans, then Homo floresiensis stops looking like an impossible outlier and starts looking like one of many experiments in being human. That changes the kinds of questions we ask. Instead of how could they exist at all, we ask how many other versions like this did we miss? So what are the most productive open questions now? Can we obtain any genetic or proteomic signal from hobbit remains or sediments that pins down their closest relatives? Can we find late surviving hobbit sites outside Liang that overlap more clearly with Homo sapiens horizons? Are there submerged coastal landscapes around Flores preserving evidence of contact or coexistence that dry caves don't show? And, more broadly, was Homo floresiensis a one-island curiosity, or a visible tip of a much larger, mostly hidden pattern of small-bodied humans scattered across the ancient archipelagos of Southeast Asia? Until we answer those, the case stays open, not as a frustrating lack of closure, but as a live, evolving investigation into just how many ways there have been, and maybe could still be, to be human. When you step back from all the details, what do we actually know about these 3-foot humans? First, they were real. Not diseased Homo sapiens, not a one-off medical anomaly. Their anatomy is internally consistent. Tiny bodies, chimp-sized brains, long arms, flared pelvises, weird feet, and wrists that look more ancient than ours. Those traits show up across multiple individuals in different ages and both sexes. That's not what pathology looks like. That's what a stable breeding population looks like. Second, they sit in a very uncomfortable place on our family tree. Their skull shape and wrists whisper very old hominin, like something closer to Homo habilis, or even late Australopithecines. Their stone tools and hunting behaviour shout, later Homo, capable of planning, cooperation, and long-term adaptation. Their timeline ties them to a 700,000-year story on Flores that starts with a taller ancestor and ends in extreme dwarfing. Every line of evidence you pick up points in a slightly different direction. Ancient branch, island, shrunk, Homo erectus, a ghost lineage tied to Denisovans or some other archaic population we've barely sampled. The honest answer is that they don't fit neatly anywhere we'd like to put them. The same goes for their disappearance. We've seen the main theories, massive eruptions and ash fall turning Flores into a short-term death trap, slower environmental shifts squeezing a fragile island food web, competition, direct or indirect, with newly arrived Homo sapiens, and the brutal arithmetic of small populations where bad luck and inbreeding can finish what ecology starts. There are hints for each. Volcanic layers bracket the last Hobbit levels. Faunal turnovers suggest ecosystems in flux. The broad regional pattern shows Homo sapiens arriving and other humans vanishing on an all-too-familiar schedule. But none of it lines up into a smoking gun. The archaeological gap is real, but whether it records a sudden cliff or a blurred, extended fade-out is still up for grabs. And that might be the most important lesson Flores gives us. Evolution in isolation can do astonishing things. It can shrink a human lineage to half its previous height, retool its body for steep valleys and seasonal scarcity, and keep it going for hundreds of thousands of years with stone, fire, and social memory as its main technologies. But isolation also makes you vulnerable. One island, one chain of volcanoes, one series of unlucky years, and an entire way of being human can vanish so completely that we're arguing about it from a single cave. So now it's your turn. Given everything you've heard, what do you think Homo floresiensis were? A dwarfed Homo erectus? An even deeper branch of our genus? Or something we haven't quite imagined yet? And what ended their story on Flores? Ash clouds, climate swings, competition with us, or a slow unravelling of a tiny population stretched past its limits? Drop your theory in the comments and tell me where you're listening from. I love seeing how many different corners of the world end up sharing the same questions about deep time and strange humans. If you found this dive into the Hobbits of Flores useful or thought-provoking, consider hitting like, leaving that comment, and subscribing so you don't miss the next journey into the weirder side of our past. And if you want to go further, I've put together a book on 12 of the most surprising prehistoric secrets that completely change how we think about human origins. If you're into this kind of long-form, evidence-driven mystery, you might really enjoy it. You can find it on the website. There's a link waiting for you down in the description.